Hello there and welcome to Life Beyond Seen, where the deep past has a way of surfacing quietly, like something rising slowly through still water, patient and unhurried, asking to be noticed at last. Tonight, we're going somewhere warm, somewhere that no longer exists, at least not in the form it once held. Picture a shallow sea, but not the kind you might imagine when you close your eyes and think of ocean. No horizon stretching blue, no deep cold below. This was something closer to a warm, salty basin, hemmed in by land on most sides, the water low and thick with minerals, the air heavy and humid, the light falling flat across a surface that barely moved. This was the western edge of the ancient Tethys Sea, in what is now southern Germany, roughly 230 million years ago. The landscape around it would have been unrecognisable. The continents were still in the early stages of drifting toward the shapes we know. The sky held a sun that looked the same as ours, but looked down on a world that was not. No grass, no flowers, no birds, no mammals. The Triassic period was still in the business of rebuilding life after the catastrophic extinction that had nearly emptied the planet 50 million years before. And the things that survived and the things that evolved to fill the empty spaces were, in many cases, deeply strange. In this particular lagoon, in this warm and slightly hostile basin where the water was saltier than most creatures could tolerate, and the oxygen levels may have dipped low enough to exclude most large predators, something rested on the muddy bottom. It was flat, wide, armoured across its back and belly with a mosaic of interlocking bone. Its head was small, and its limbs were short and paddle-like, tucked close to a body that barely seemed to belong to an animal at all. It moved slowly, if it moved much at all. It had the general outline of a river stone, if a river stone had a blunt little face and a quiet sense of purpose. If you had been there, floating just above the bottom of that lagoon, and you had looked down at this creature, your first instinct would have been immediate and confident. Turtle, you would have thought. Obviously a turtle. The shape is unmistakable. The wide flat shell, the tucked limbs, the low profile, the general air of patience. Turtle. You would have been wrong. This animal was not a turtle. It was not even distantly related to turtles. It had arrived at this shape through a completely different path, across a completely different lineage, driven by pressures that had nothing to do with the pressures that would later shape the turtle body plan. It just happened to look almost exactly the same. Its name was Henodus Cheliops. The name carries a kind of quiet honesty about what scientists saw when they first described it. Henodus roughly means single-toothed, which we will come back to because the teeth, or the near absence of them, are one of the stranger things about this animal. And Cheliops means something close to turtle-faced. So even the people who named it felt the need to acknowledge the resemblance right there in the official scientific label. Turtle-faced, single-toothed. A creature that looked like one thing and was entirely another. Before we go any further into the story of this remarkable animal, I want to pause for just a moment and ask you something simple. Where are you right now as you listen to this? Are you at home, settled in for the evening, with something warm nearby? Are you somewhere cold, with the kind of dark outside that makes a story about a warm ancient lagoon feel especially appealing? What time is it where you are? Is it late? That particular hour when the day finally lets go and the mind opens up just slightly more than usual? I find that these kinds of stories, the ones that go back hundreds of millions of years, have a different quality at night. The distance becomes easier to feel. 230 million years is not a number that means much in daylight, but late at night, in a quiet room, with nothing demanding your attention, that number can settle into something almost physical. A long, long time. A world entirely unlike this one. A creature that no human being ever saw, that lived and fed and rested in a lagoon that no longer exists, in a sea that has long since rearranged itself into mountains and plains and river valleys. If this is the kind of quiet exploration you enjoy, the slow, careful kind that takes its time and does not rush past the interesting parts, I would be genuinely grateful if you gave this video a like and subscribe to Life Beyond Seen. It helps this channel reach other people who like to spend their evenings in good company with the strange and the fascinating. And there is no pressure, of course. But if the idea of spending more nights like this one sounds appealing, the subscribe button is right there, patient as Henodus on the lagoon floor. Now, the story of this creature begins not in the Triassic, not with the animal alive in its warm basin, but much later. It begins in 1936 in the Tübingen region of southern Germany, with a paleontologist named Friedrich von Huene kneeling over a slab of very old rock. Von Huene was not a young man at this point. He had been working in paleontology for decades and had already made a substantial name for himself. He was one of the most prolific dinosaur namers of the 20th century, responsible for describing dozens of species across multiple continents. He was the kind of scientist who seemed to find important things wherever he looked, partly because he was skilled and partly because he worked with extraordinary persistence across an enormous range of sites and formations. By the time he arrived at the Tübingen excavation in 1936, he had already seen a great deal of the fossil record. He was not easily surprised, and yet, when the rock gave up what it had been holding, he knew immediately that this was something different. The formation where the fossil was found is called the Gipskuper. It is a Triassic age deposit, fine-grained and pale, the kind of sedimentary rock that forms in quiet, shallow water conditions. The word gyps in the name refers to gypsum, which is a mineral that forms when water evaporates and leaves its dissolved salts behind. The presence of gypsum in a rock formation is a message from the past. It says the water here was warm and shallow and salty, possibly hypersaline, meaning saltier than normal seawater. It says the environment was stressed and unusual. It says that whatever lived here was adapted for conditions that most creatures would have found intolerable. Fine-grained limestone and gypsum-bearing deposits are, from a paleontologist's perspective, among the best kinds of rock for finding well-preserved fossils. The sediment settles slowly and gently. There is no violent current to scatter bones. The chemistry can be right for mineralization. What goes in sometimes stays in remarkable detail. What von Huene found in the Gipskuper was nearly complete. That word, complete, does not always mean what it sounds like in paleontology. Often a nearly complete skeleton means perhaps 60 or 70% of the bones are present and in rough order. In this case, the Henodus specimen was unusually intact. The wide, flat carapace was there, the skull was there, the limbs were there. Enough of the animal had survived 230 million years of burial, compression, and geological change that von Huene could look at it and understand its basic shape with confidence. He named it, described it, and published his findings. The scientific community received the description with a certain kind of puzzled attention. Here was an animal that looked, on first inspection, like a turtle. But when von Huene examined the anatomy carefully, the lineage did not line up. The bones were not arranged the way turtle bones are arranged. The shell was not built the way a turtle shell is built. The skull had a different structure, and the teeth, or the near-total absence of them, were unlike anything in the turtle line. Henodus cheliops was something else entirely. It was a placodont. And if that word is unfamiliar, that is understandable. Placodonts are not the kind of prehistoric animal that tends to make it onto posters or into documentaries. They are not as dramatic as the large predatory dinosaurs, not as immediately arresting as a long-necked plesiosaur or a massive ichthyosaur. They are in some ways the quiet corner of the Triassic marine world. But what they represent, and what Henodus in particular represents, is one of the most interesting evolutionary stories the fossil record has preserved. The fact that von Huene recognised the strangeness of the fossil immediately says something about the quality of the specimen and the quality of the scientist. A less experienced eye might have looked at the flat carapace and the overall silhouette and simply filed it away as an unusual turtle variant. Von Huene looked deeper. He saw the structural differences. He understood that resemblance and relationship are not the same thing. and in doing so he opened a question that paleontologists have been exploring ever since. How does an animal that is not a turtle end up looking almost exactly like one? How does evolution arrive at the same solution twice, through completely different pathways, separated by millions of years? And what does that tell us about the logic of life itself? Those are the questions that make Henodus worth spending an evening with, not just because it was a strange-looking creature in a strange-looking world, but because it is a kind of argument written in bone. An argument that nature, when faced with certain problems, tends to reach for certain answers. That the turtle shape, flat and armoured and low to the ground, is not an accident or a quirk, it is a solution. And more than one lineage, working independently in different eras, from different starting points, eventually found it. Von Kuhn could not have known all of that in 1936. The tools for understanding it, the phylogenetic analyses, the CT scanning, the detailed comparative anatomy, were still decades away. But the fossil he pulled from the Gipskuiper that year was the beginning of the conversation. A single specimen, a single creature, preserved by luck and chemistry, and the particular quiet of a hypersaline lagoon, sitting in the rock for 230 million years, waiting to be found by exactly the right person at exactly the right time. And now that we have found it too in our own way, it is worth taking the time to understand what it actually was. Not just what it looked like, but what group it belonged to, where that group came from, and why a lineage of marine reptiles in the Triassic period ended up looking more like turtles than most of the animals we actually call turtles. That story begins with the placodonts themselves, and with a broader group of Triassic marine reptiles that were in many ways the first serious attempt by vertebrate life to colonize the sea after the catastrophic emptying of the Permian extinction. It is a story about opportunity, about open ecological space, about what happens when the rules of survival are suddenly rewritten and life has to improvise. And Henodus, resting quietly at the bottom of its warm and salty lagoon, is one of the most interesting improvisations that story ever produced. Friedrich von Kuhn was not a young man when he found Henodus. By 1936 he was already in his 60s, and he had been doing this kind of work for most of his adult life. He had named more than a dozen dinosaur species, including some of the earliest known sauropodomorphs from South America and Europe. He had spent decades in the field, in the laboratory, in the literature, building a reputation as one of the most thorough and productive vertebrate paleontologists of his generation. When he arrived at the Triassic deposits near Tübingen in the mid-1930s, he was not a man easily surprised by what the rock gave up. He had seen a great deal, and yet the animal he found in the Gipskuiper stopped him. Tübingen itself is a university town in the Baden-Württemberg region of what is now southwestern Germany. It sits on the Neckar River, surrounded by gentle hills and old forests, the kind of European landscape that looks as though it has been quietly settled and resettled for so long that even the farmland feels historical. The Triassic outcrops in the region are not dramatic. They do not form towering cliffs or vast canyon walls. They emerge in road cuts, quarry faces and riverbanks, pale grey and yellowish, easy to overlook if you do not know what you're looking for. The Gipskuiper Formation, which takes its name from the German word for gypsum, runs through this part of Germany as a geological layer from the Late Triassic period, roughly 235 to 225 million years old. It is a formation made of fine-grained carbonate sediments, mudstones, and those distinctive gypsum deposits that speak to an ancient evaporating sea. The conditions that produced the Gipskuiper were, in geological terms, fairly unusual. This was not an open ocean deposit. It was the kind of sediment that accumulates in restricted, shallow basins, where water evaporates faster than it is replenished. The chemistry of such environments is hostile to most life, but it is extraordinarily good for preservation. When an organism dies in a low oxygen, high salinity lagoon and sinks gently into fine sediment, it does not get torn apart by scavengers or scattered by currents. It settles, it mineralizes, it waits. and the fine grain of the surrounding rock records its outline with a fidelity that coarser sediments simply cannot match. This is the context in which von Huene found his specimen. Not in a dramatic canyon or a celebrated fossil bed already famous among scientists, but in the quiet, unglamorous geology of southern Germany, in a formation that most people would walk past without a second glance. The excavation was careful work. Paleontological fieldwork in carbonate rocks of this type requires patience, because the fossil and the matrix can be difficult to distinguish until you are already quite close to the bone. The work moves slowly, with fine tools, constant attention, and the kind of practiced eye that only decades of experience produce. What came out of the rock was, by any standard, a remarkable find. The specimen was nearly complete in its overall layout. The wide, flat carapace preserved across most of its area, the skull present and largely intact, the limb elements in place, the plastron, the belly armour also preserved. For a Triassic vertebrate, this level of completeness is not something you can count on. Most Triassic marine reptile fossils are fragmentary. Isolated bones, partial skulls, scattered vertebrae. A nearly complete articulated skeleton from this period is the kind of thing a paleontologist might wait an entire career to find. Von Huene was experienced enough to understand immediately what he was looking at in terms of preservation quality. The specimen was exceptional. What it actually was, taxonomically and biologically, was another matter entirely. When von Huene examined the anatomy of the fossil carefully, the first thing that struck him was the shell. It was present, it was wide, it was flat, and at a glance it resembled the carapace of a turtle. But the structure was wrong. A turtle's shell is a deeply integrated part of its skeleton. The dorsal shell, called the carapace, is formed from the fusion of the turtle's own ribs, vertebrae, and a series of dermal bones. It is not a separate structure sitting on top of the animal. It is the animal's back, reorganized and expanded over millions of years of evolution into a protective dome. The shell of the creature von Huene was looking at was built differently. It was a mosaic of small, separate bony plates, osteoderms, embedded in the skin and arranged across the back and sides of the body. These are not fused ribs. They are not reorganized vertebrae. They are an independent bony armour that developed in the skin itself through a completely different developmental and evolutionary process. Von Huene recognized this difference. He also noted the skull, which was wide and flat and had a distinctly non-turtle architecture. The teeth, or rather the almost complete absence of them, were another signal. A single small tooth on each side of the jaw, and otherwise a wide, flat beak. This was not the dentition of any turtle lineage he knew. It was not the dentition of any archosaur, it was something else. He named the animal Henodus Keliops. The genus name comes from the Greek, roughly translating to single-toothed, a reference to that unusual near-toothless jaw with its solitary lateral teeth. The species name Cheliops means turtle-faced, which is an honest acknowledgement of the obvious resemblance that could mislead a casual observer. Von Huene published his formal description in 1936, and the paper introduced the scientific community to an animal that did not fit neatly into any existing category. The reaction from other researchers was predictably a mixture of fascination and caution. Here was an animal that looked like a turtle but was not a turtle. It looked armoured and aquatic, but it was not a turtle, not an archosaur, not anything that could be easily slotted into the established mental maps of Triassic life. The question of what it actually was, in terms of its evolutionary relationships, would take decades of subsequent work to answer with any confidence, and even now, certain aspects of its biology remain genuinely open. What eventually became clear through comparative anatomy, and later through more rigorous phylogenetic analysis, was that Henodus was a placodont. More specifically, it belonged to the siamodontoid branch of placodonts, the armoured lineage within a group that was itself already somewhat obscure in the popular understanding of prehistoric life. Placodonts are not the animals that feature in most books about the Mesozoic. They are not the long-necked plesiosaurs that appear in museum reconstructions. They are not the streamlined ichthyosaurs. They are something quieter, stranger, and in many ways more interesting precisely because they are less familiar. To understand why von Huyn's find mattered so much, and why it continues to matter, it helps to sit with the basic fact of what he had uncovered. He had found an animal from 230 million years ago that had, through its own evolutionary history, arrived at a body plan strikingly similar to that of turtles, despite being entirely unrelated to turtles, despite building its shell through a completely different biological mechanism, and despite living in a world where the turtle lineage had not yet become the dominant armoured reptile of the seas. The resemblance was not ancestry, it was not imitation, it was convergence, the independent discovery of the same solution by two separate lineages working from different blueprints. Von Huyn understood this in broad terms. He knew the animal was not a turtle. He knew it was something separate. But the full theoretical weight of what that meant, the implications for understanding how evolution works and why certain body shapes keep appearing across unrelated groups, was something that would be developed by later researchers, working with more sophisticated tools and a fuller understanding of the Triassic world. What he had done, in practical terms, was pull a single specimen from a pale limestone outcrop in southern Germany and hand the scientific world a puzzle that is still being turned over today. The holotype specimen of Henodus Keliops, the one and only individual we have ever found, is housed in collections associated with the University of Tübingen. It has been studied, photographed, measured and reanalyzed multiple times since 1936. Each generation of researchers has brought new questions to it and extracted new answers, sometimes revising what earlier scientists concluded. That is the nature of paleontology, really. A fossil does not give up all its information at once. It answers the questions you know how to ask, and as the questions get better, the fossil gets more interesting. The Henodus specimen has been asked about its shell structure, its jaw mechanics, its phylogenetic position, its bone density, its likely habitat, and its relationship to other placodonts. Each inquiry has added a layer to the picture. None of them has made the animal less strange. There is something worth pausing on here, which is the sheer duration of time between the animal's life and its discovery. Henodus lived approximately 230 million years ago. It died in a warm, shallow, hypersaline lagoon in what would eventually become southern Germany. Its body settled into fine sediment. The sediment compacted over millions of years into limestone. The limestone was buried, tilted by geological forces, and eventually brought back toward the surface by the slow, patient work of erosion and uplift. And then, in 1936, a German paleontologist in his 60s walked up to an outcrop of pale rock and found it. That gap, 230 million years, is almost impossible to hold in the mind as a real number. It is easier to think of it simply as a very long time, long enough that the continents have moved, the oceans have rearranged themselves, entire lineages of life have appeared and vanished, and the world has been remade several times over. Through all of that, the fossil waited. Von Huyn's role in the story is worth appreciating not just for what he found, but for what he did with it. He did not misidentify it as a turtle and move on. He looked carefully enough to see the structural differences. He named it accurately, gave it a name that acknowledged both its strangeness and its turtle-like appearance, and he published a description thorough enough that subsequent researchers could work from it. That is not a small thing. The quality of an original fossil description can determine how well understood an animal is for generations. A careless or incomplete description can mislead researchers for decades. Von Huyn's description was careful. He died in 1969, having named more than 200 species of fossil vertebrates over the course of his career. Henodus Keliops is not the most famous of them, not the one that appears in the textbook summaries of his work, but it is arguably one of the most conceptually interesting because it sits at the intersection of several of the deepest questions in evolutionary biology. How does convergence happen? What does it tell us about the constraints and possibilities of life? Why do certain shapes keep appearing in different eras, in different lineages, in different oceans? Those questions were not fully formed in 1936. They have sharpened considerably since then. And they lead, naturally and inevitably, into the group that Henodus belonged to, because the placodonts as a whole are one of the more remarkable evolutionary experiments the Triassic period produced. To understand what Henodus was and why it looked the way it did, you have to understand where it came from within that group, what the earlier placodonts looked like, and how the lineage moved over the course of roughly 40 million years, from robust lizard-like creatures with flat crushing teeth to something that a casual observer in 2024 might genuinely mistake for a large, unusual turtle resting on the bottom of a shallow sea. That journey through placodont evolution is where the story goes next. And it is a journey that turns out to have a great deal to say about how life responds to open ecological space, to predator pressure, and to the particular demands of a warm, shallow Triassic sea. Placodonts are not a name that comes up often outside of paleontology circles, and that is a shame because as a group they represent something genuinely unusual in the history of vertebrate life. They were marine reptiles of the Triassic period, appearing in the fossil record around 245 million years ago, and disappearing entirely at the end of the Triassic, roughly 201 million years ago. That gives them a run of about 44 million years, which sounds long until you compare it to, say, crocodilians, which have been around for over 80 million years and are still here, or turtles, which have been doing their slow and armoured thing for even longer. In geological terms, placodonts were a relatively brief experiment, but what an experiment it was. To place them properly, placodonts belong to a larger group called Sauropterygia. That name covers a wide range of Triassic and Mesozoic marine reptiles, and it includes some animals that are considerably more famous than placodonts. Plesiosaurs, for instance, were Sauropterygians, those long-necked, large-bodied marine reptiles that patrolled Jurassic and Cretaceous seas and that have been inspiring lake monster legends ever since, are part of the same broad lineage. Placodonts, however, branched off early in the history of that group. They did not lead to plesiosaurs. They were a separate experiment running alongside the lineage that would eventually produce them. Think of it less like a family tree, where one thing becomes another, and more like two branches growing from the same point on a trunk, each going in its own direction. The name placodont comes from the Greek for flat teeth, which tells you something immediately about the group's defining characteristic. The early placodonts were built around their dentition. They had large, flat, rounded teeth arranged in the roof of the mouth and along the lower jaw, teeth designed specifically for crushing hard-shelled prey. Mollusks, bivalves, crustaceans, anything with a shell that needed to be broken open before it could be eaten. Picture the teeth of a modern wolf eel, or the crushing plates in the throat of a drumfish, and you have something in the right neighbourhood. These were not teeth for tearing meat or shearing through soft tissue. They were millstones, biological grinders, and the jaws that held them were correspondingly robust, built to generate the force needed to crack shells that had evolved specifically to resist being cracked. One of the earliest and best-known placodonts is Placodus, which lived around 245 million years ago in the shallow seas of what is now Central Europe. Placodus looked nothing like a turtle. It was a fairly large animal, roughly 2 meters long, with a stocky lizard-like body, 4 solid limbs and a long tail. It had no shell, no armour, no carapace. It moved through shallow water using its limbs and tail, probably in a way not entirely unlike a large modern monitor lizard swimming, though it was better adapted to water than most monitors are. The defining feature was those teeth. Placodus had projecting front teeth for prying shellfish off rocks, and large flat back teeth for crushing them. It was, in essence, a very effective shellfish-eating machine in a generalist reptile body. What is interesting is that Placodus was not particularly armoured. It had some small bony nodules along its back, which may have provided a little protection, but nothing that would have stopped a determined predator. It was relatively mobile, relatively exposed, and it lived in environments where other large marine reptiles were also present. Nothosaurs, for instance, were around at the same time. Nothosaurs were long-necked, fish-eating reptiles, some of them quite large, and they shared the Triassic seas with early placodonts. The presence of active predatory animals in the same waters that Placodus inhabited would have created real pressure on any slow, bottom-feeding reptile. Over the course of the Triassic, one branch of the placodonts began responding to that pressure in a very particular way. This branch is called the Siamodontoids, and they are the armoured placodonts. Starting from a body plan not entirely unlike Placodus, the Siamodontoids progressively developed heavier and more extensive bony armour over their backs and eventually their bellies. The mechanism for this armour was osteoderms, which are small bony plates that form within the skin itself. Osteoderms are not unique to placodonts. Crocodilians have them, many lizards have them, some dinosaurs had them. They're a fairly common vertebrate solution to the problem of needing protection, without completely rebuilding the skeleton. In placodonts, though, the osteoderms became increasingly elaborate over time, eventually fusing into a continuous mosaic that covered the back and sides of the animal in something resembling a shell. Siamodus is a good intermediate example. It lived during the Middle Triassic, somewhat earlier than Henodus, and it had a well-developed dorsal shield, a broad bony covering over its back formed from fused osteoderms. It still had the characteristic crushing teeth of the placodonts, still had a reasonably robust body, but the shift toward a more protected, more armoured form was clearly underway. Looking at Siamodus, you can see the trajectory. The body's getting flatter, the armour is getting more extensive, the overall shape is becoming less like a swimming lizard and more like something that spends its time close to the bottom, not racing through open water. Henodus, appearing somewhere around 230 to 228 million years ago, sits at the far end of this trajectory. It is the most extreme development of the armoured placodont trend. By the time you get to Henodus, the osteoderms have formed a complete carapace over the back and a plastron covering the belly. The limbs have become more paddle-like, the tail has shortened, the skull has flattened, and the teeth have been reduced to almost nothing. The animal has travelled over the course of roughly 15 million years of placodont evolution, from something like Placodus to something that looks, to any reasonable observer, like a turtle. And it did this entirely independently of the turtle lineage, using different developmental tools from a different starting point in a different part of the evolutionary tree. That is the thing that keeps drawing researchers back to placodonts in general, and to Henodus in particular. The convergence is not approximate or superficial, it is deep and structural. The overall body plan, the broad flat shell, the low profile, the paddle limbs, the short tail, the beak-like jaw, these are not coincidental similarities in the way that, say, two unrelated fish might have a similar colour. They are fundamental architectural similarities in animals that arrived at them through completely different biological routes. And this raises a question worth sitting with for a moment, which is why? Why does this particular body plan keep appearing? What is it about a flat, armoured, slow-moving, bottom-dwelling form that makes it such an attractive solution for aquatic animals in certain environments? The answer involves several things working together. Shallow water environments, particularly warm, coastal, or lagoonal habitats, tend to have abundant benthic prey, meaning prey that lives on or near the bottom. Mollusks, crustaceans, worms, and various invertebrates concentrate in these zones. An animal that can stay close to the bottom and harvest this food source has access to a reliable and often dense resource. But staying close to the bottom in shallow water also means being relatively visible and relatively slow. You're not going to outswim a predator, so protection becomes more valuable than speed. A wide, flat body pressed close to the substrate is actually harder for a predator to get purchase on than a rounded or elongated body. There is less to grab, less exposed surface area that a predator can attack from the side or above. A shell or shell-like armour adds another layer of protection, and a low, wide profile reduces the animal's visual signature from above, which matters in shallow, well-lit water where aerial or surface predators might also be a threat. All of these pressures point toward the same solution, independently, in different eras, in different lineages. The turtle lineage found this solution. The placodont lineage found it. And they found it in ways that are structurally parallel but mechanistically distinct. The turtle shell is a genuinely unusual structure in vertebrate anatomy. It is not simply a layer of armour bolted onto the outside of a normal reptile body. It is the body, reorganised. The ribs of a turtle are fused to the inside of the shell. The shoulder blades sit inside the rib cage rather than outside it, which is unique among vertebrates. The whole skeletal architecture has been rearranged around the shell in a way that took millions of years to develop and that required significant changes to how the animal breathes, moves, and grows. It is an elegant solution, but it is a costly and complex one, and it required the turtle lineage to fundamentally rebuild its body plan from the inside out. Placodonts did something different. They kept their basic skeletal architecture and added armour on top of it, growing bony plates within the skin that gradually spread and fused into a continuous covering. The underlying skeleton was not reorganised in the way a turtle's is. The ribs were still ribs. The shoulder blades were still in a normal position. The shell was an addition, not a reconstruction. The result looked similar from the outside, but the internal logic was entirely different. Two separate routes to the same destination. That is convergent evolution in one of its clearest and most dramatic forms. Biologists find convergent evolution fascinating for a reason that goes beyond the immediate strangeness of it. It suggests that evolution is not simply a random walk through possibility space, trying out shapes at random and occasionally landing on something that works. It suggests instead that certain shapes are, in some sense, preferred by the physics and ecology of the environments that produce them. That there are attractors in the landscape of possible animal forms, regions of design space that natural selection keeps finding its way back to because they work particularly well under particular conditions. The flat, armoured, bottom-dwelling aquatic body plan is apparently one of those attractors. It has been discovered at least twice in reptile evolution, probably more if you count some of the armoured fish lineages and various invertebrate designs that converge on similar forms. There is a parallel that gets cited frequently in discussions of convergent evolution, which is the similarity between ichthyosaurs and dolphins. Ichthyosaurs were Mesozoic marine reptiles, completely unrelated to mammals, that evolved a streamlined, fish-like body with a dorsal fin, a crescent-shaped tail fin, and flipper-like limbs. Dolphins, which are mammals, evolved the same overall shape independently, driven by the same hydrodynamic pressures of fast open water swimming. The convergence is striking enough that photographs of ichthyosaur skeletons next to dolphin skeletons have become a standard illustration in evolutionary biology textbooks. Henodus and turtles represent a different version of the same phenomenon, slower, more sedentary, more heavily armoured, but equally clear in its demonstration that similar environments produce similar animals regardless of ancestry. What makes the Henodus case particularly interesting, and slightly different from the ichthyosaur-dolphin comparison, is the timing. Ichthyosaurs and dolphins are separated by a vast stretch of time, but they existed in broadly similar oceans, subject to broadly similar predation pressures and hydrodynamic constraints. Henodus, however, lived roughly 30 million years before the marine turtle radiation really got underway. The sea turtle lineage as we know it, the large ocean-going, fully marine turtles, became prominent much later in the Mesozoic. Henodus was not responding to the same world that marine turtles eventually inhabited. It was responding to a specifically Triassic world, with Triassic predators, Triassic prey, and Triassic ocean chemistry. The fact that it arrived at a similar solution anyway, across that temporal gap and in a different ecological context, makes the convergence even more striking. It also raises an interesting point about what the turtle body plan actually represents. If two completely separate lineages, working from different starting points, in different time periods, with different developmental tools, both arrived at something resembling a turtle, then perhaps the turtle body plan is not just a successful design, but something close to an optimal one for a certain kind of aquatic lifestyle. Not the only solution, not inevitable in any strict sense, but strongly favoured by the logic of shallow water, benthic, slow-moving life. The turtle lineage has been around for over 200 million years and shows no signs of going anywhere. The placodonts lasted 44 million years before the end Triassic extinction removed them. But the fact that they existed at all, that they got so far down the same evolutionary road, suggests that the road itself is a real one, not just a path that one lucky lineage happened to stumble onto. All of this theoretical weight rests on a group of animals that most people have never heard of, and on one animal in particular that most people, if they saw a reconstruction of it, would immediately call a turtle and move on. That is part of what makes Henodus worth spending time with. It is not famous. It is not dramatic in the way that a large predatory dinosaur is dramatic. It was a metre-long, slow-moving, bottom-feeding animal in a warm lagoon, and it has been known from a single specimen for nearly 90 years. But the questions it raises about convergence, about the logic of natural selection, about the range of forms that life can independently discover, are among the more interesting questions in evolutionary biology. And those questions become sharper when you look at the specific physical details of Henodus, because the animal itself, examined closely, is full of surprises. The shell is not quite what you might expect. The skull is strange in ways that go beyond just looking like a turtle's skull. The teeth, or rather the near-total absence of them, raise a feeding mystery that researchers have not fully resolved. The body as a whole, when you look at it carefully rather than just noting the general turtle-like impression, turns out to be a more peculiar and specific thing than the quick glance suggests. The physical reality of Henodus, measured and described in detail, is where the story gets more concrete, and it is where the next layer of questions begins to open up. So let us slow down and look at the physical animal itself, not the concept, not the evolutionary category, not the theoretical framework of convergent evolution, but the actual creature. The one that von Huene pulled out of the Tübingen limestone in 1936, nearly complete, lying flat in the rock the way it had been lying for 230 million years. Henodus was small. That surprises people sometimes, because the shell gives an impression of bulk and solidity. But the animal was roughly 1 metre in length, nose to tail, which puts it in the range of a large domestic cat or a medium-sized snapping turtle. Not imposing, not threatening. The kind of animal you might almost step over if you weren't paying attention, though the weight would have been deceptive. All that armour adds up. The most immediately striking feature was the carapace, which is the technical term for the upper shell. In most turtles, the carapace is roughly oval, longer than it is wide, with a gentle dome to it. Henodus was different. The carapace was nearly square in outline, and it was wide, disproportionately wide relative to the length of the body. Some reconstructions suggest it was actually wider than it was long, giving the animal a flattened, almost pancake-like silhouette when viewed from above. Not a dome, not a rounded hump, more like a broad, flat platform pressed close to the ground. The shell surface itself was not smooth. This is one of the details that distinguishes Henodus most clearly from a turtle at close range. In turtles, the carapace is formed from large, clearly defined scutes, arranged in a specific pattern, with the underlying bone organised into fused ribs and vertebrae. The surface has a particular geometry to it, recognisable and consistent across the turtle lineage. Henodus had none of that. The surface of the carapace was a mosaic of small, irregular polygonal bones, osteoderms, each one fitting against its neighbours in an interlocking pattern that covered the back like a kind of biological cobblestone pavement. The individual pieces were not large. They were not organised into neat rows. They fitted together in a dense tiled arrangement that would have given the shell a rougher, more textured surface than a typical turtle's. If you ran your hand across a living Henodus, you would have felt something closer to a rough stone wall than a polished shell. Underneath, there was also armour, The plastron, the ventral shell that covers the belly, was present in Henodus, which is another feature shared with turtles but arrived at independently. This is significant because not all armoured placodonts had a fully developed plastron. Some had partial ventral coverage. Henodus had a more complete one. Being armoured on top and bottom simultaneously suggests a lifestyle where threats could come from multiple directions, or alternatively, that the ventral armour provided structural support and protection during movement across hard substrate. Either way, it represents a further commitment to the fully enclosed body plan. The skull was small relative to the carapace. Proportionally, it looked almost like an afterthought, this narrow, flat little head emerging from the front edge of the wide shell. The skull was broad and somewhat flattened, not deep and robust the way a predatory animal's skull tends to be. The eye sockets were positioned toward the sides and slightly toward the top of the skull, which is a placement associated with animals that spend time looking upward from the bottom of a water column, watching for movement above them rather than scanning forward. The nostrils were positioned near the front of the snout, fairly high up, consistent with an animal that surfaces briefly to breathe and then descends again. The limbs were paddle-like, not fully modified into flippers the way a sea turtle's limbs are, where the bones are locked into a rigid, flat structure optimized purely for swimming. Henodus had limbs that were in an intermediate state, broader and flatter than the limbs of a typical land reptile, with modifications that suggest regular use in water, but retaining enough flexibility that some researchers have suggested the animal could haul itself onto mud flats or shallow shores when needed. Think of it less like a sea turtle, which is almost helpless on land, and more like a large freshwater turtle, which can manage both environments with varying degrees of awkwardness. The tail was short, very short. In many reptiles, the tail serves as a counterbalance, a rudder, a weapon, or a fat storage organ. Henodus had almost none of it to speak of. A short, stubby tail behind the rear edge of the shell, contributing little to propulsion and probably not much to steering. This is consistent with an animal that was not a fast or agile swimmer. It did not need a powerful tail because it was not chasing prey or evading predators through open water. It was moving slowly, close to the bottom, in shallow water where speed was not the primary survival strategy. When you put all of these features together, what you get is an animal that was almost entirely committed to a single ecological mode. Low to the ground, heavily protected, slow-moving, bottom-associated, with sensory organs positioned to monitor what was above it rather than what was in front of it. The body is not the body of an opportunist, it is the body of a specialist. Every architectural choice, the wide flat shell, the short tail, the paddle limbs, the heavy ventral armour, the small head with elevated eyes, points toward the same lifestyle, sitting on or near the bottom of shallow water, moving slowly and being very difficult to eat. The weight of all that bone deserves a moment of consideration. Bone is dense, osteoderms are solid. A complete upper and lower shell of interlocking bony plates, covering an animal from head to tail and from back to belly, represents a significant investment in calcium and structural material. This would have made Henodus heavy for its size, heavier than a comparably sized unarmoured reptile, and that heaviness had a hydrodynamic consequence that is actually useful for a bottom-dwelling animal. Dense, heavy animals tend to be negatively buoyant in water, meaning they naturally sink rather than float. For an animal that wanted to stay close to the bottom of a lagoon, that is an advantage. You do not have to work to stay down. Gravity and density do it for you. You only need to expend energy when you want to move horizontally or rise to the surface to breathe. Modern analogues exist for this kind of lifestyle, and they are instructive. The common snapping turtle, Chelydra serpentina, is a large freshwater turtle that spends most of its time on the bottom of ponds, rivers and lakes. It moves slowly, it is heavily built, it is not a graceful swimmer, it waits, it ambushes, it scavenges, and it is very difficult to injure because its shell and sheer mass make it formidable despite its lack of speed. There is also the alligator snapping turtle, Macrocheles teminki, which is even more extreme in this direction. A massive, armoured, bottom-sitting animal that barely needs to move to feed. Neither of these animals is closely related to Henodus, of course, but they occupy a similar ecological position, and their body plans carry a similar logic. Heavy, armoured, slow, bottom-associated, difficult to kill. The weight implications also affect how we think about Henodus on land. If it could haul itself ashore at all, it would have moved slowly and with considerable effort. The paddle limbs, while functional in water, were not designed for efficient terrestrial locomotion. On land, Henodus would have been vulnerable in a way it simply was not in water. The armour that made it nearly invulnerable in a shallow lagoon would have been a liability on shore, adding weight without adding speed. This suggests that any time Henodus spent on land was probably brief and purposeful, perhaps for egg-laying, perhaps for moving between water bodies during dry periods, but not for extended terrestrial activity. There is also the question of how Henodus grew. We have one specimen, one adult, or near-adult, individual. We do not have juveniles. We do not have a growth series. This means we cannot say with confidence how fast Henodus grew, how long it lived, or what it looked like at different stages of its life. In many modern turtles, juveniles are more vulnerable because the shell is not yet fully hardened. It is reasonable to suppose that juvenile Henodus individuals were similarly more exposed before the full osteoderm mosaic had developed and fused. But this is inference, not observation. The single specimen limits us in ways that are genuinely frustrating for researchers. What the specimen does tell us in its careful, detailed preservation is that Henodus was a thoroughly committed animal. There is nothing tentative about its body plan. This was not an animal in the early stages of evolving armour, testing out a few osteoderms and seeing how they worked. This was the finished product, or close to it, a fully realised version of the armoured, bottom-dwelling, shallow-water lifestyle. The mosaic was complete, the plastron was present. The limbs were modified, the skull was flat and the tail was reduced. Everything about the body said, "This is what I am, and I have been this for a while." And yet, for all the clarity of the body's commitment to this lifestyle, there is one feature that does not fit the expected pattern. One thing that makes Henodus genuinely strange even within the context of its own group, even compared to other armoured placodonts, even compared to the turtles it superficially resembles. And that is the teeth, or rather, the almost complete absence of them. Most placodonts were, as the name suggests, plate-toothed animals. Large, flat, pavement-like teeth arranged in the jaws for crushing hard-shelled prey. Mussels, clams, oysters, crustaceans, anything with a hard external skeleton that other animals struggled to process. The teeth were the defining feature of the group, the thing that gave them their ecological identity. They were the shellfish specialists of the Triassic marine world, and their teeth were the tools that made that specialization possible. Henodus had almost none of this. The name itself tells you something is wrong. Henodus means something close to single-toothed, and while that is a slight simplification, it is not far from the truth. There was a single small tooth on each side of the jaw, lateral teeth, modest in size, nothing like the broad crushing plates of its relatives. The rest of the jaw was occupied by a wide, flat, keratinous beak, a structure made of the same tough protein that forms bird beaks and turtle beaks, and the claws of mammals. Hard, but not hard in the way teeth are hard. Useful for cutting and pressing and scooping, but not for the heavy-duty crushing that placodont teeth were built for. This is where the physical description runs directly into a mystery that researchers have not yet resolved, and it is a mystery worth sitting with for a moment before moving on. Because the body of Henodus, examined closely and carefully, turns out to be a specific and detailed thing, not just a general turtle shape, but a precise set of physical choices that point toward a very particular way of living. And the teeth, or the lack of them, are the one feature that does not fit the obvious story. They are the part that makes you stop and ask what this animal was actually doing with its days. What was it eating? How was it finding food? And what does the near-toothless jaw tell us about a life spent in a warm, shallow, hypersaline lagoon at the edge of the Triassic world? So let us spend a little time with the body itself, because Henodus, as a physical object, as a shape in the world, is worth examining carefully. Not just in the abstract sense of noting that it had a shell and some limbs, but in the specific, detailed sense of understanding what it actually looked like, how it was proportioned, what it would have felt like to place your hand on its back if you could somehow reach across 230 million years and do such a thing. The overall size was modest. Henodus was roughly 1 metre in length, give or take depending on how you measure the specimen and account for soft tissue that did not preserve. That is about the length of a large domestic dog or a reasonably sized snapping turtle. Not enormous, not small either, for a shallow water bottom dweller. At 1 metre, it was large enough to be difficult for most predators to swallow, and heavy enough that simply moving it would have required real effort. But it was not the kind of animal that dominated its environment through sheer mass. It dominated through architecture. The carapace, the upper shell, was wide. Strikingly wide. In some reconstructions, it appears nearly as wide as it was long, giving the animal a silhouette that is almost square when viewed from above. This is unusual even among heavily armoured animals. Most shelled creatures, turtles included, tend toward an oval or elongated oval outline. The near-square shape of Henodus suggests something specific about how it moved, or more accurately, how little it needed to move quickly. A wide, flat body is not hydrodynamic. It does not cut through water efficiently. It sits in water. It presses against the bottom. It is stable rather than swift, a platform rather than a projectile. The width also meant that the animal presented a very large, very flat surface to anything approaching from above, which in shallow water is the direction most threats would come from. The shell itself was not a smooth dome. This is one of the details that separates Henodus clearly from turtles even when you're looking directly at the fossil. A turtle's shell, particularly the upper carapace, tends toward a relatively smooth or gently ridged surface, formed from the fusion of expanded ribs and vertebrae with overlying scute plates. It is a unified structure, bones grown together into something that functions as a single piece. The shell of Henodus was different in texture and in origin. It was formed from a mosaic of small polygonal osteoderms, those bony plates embedded in the skin, arranged in an interlocking pattern across the back. The result would have looked less like a smooth dome, and more like a surface of fitted tiles or cobblestones, each piece distinct, the whole held together by the way the pieces locked against each other, rather than by full fusion into a single bone. Imagine, if you can, the texture of a dry riverbed when the mud has cracked into irregular polygonal sections, or the pattern on the back of some monitor lizards where the scales form a kind of mosaic. The surface of Henodus would have had something of that quality, a rough, tiled, slightly irregular surface that would have felt hard and uneven under your hand. Not smooth like a polished stone, more like a carefully fitted floor made of slightly different sized pieces. The seams between the osteoderms would have been visible, giving the shell a patterned appearance that was probably quite distinctive in life. The plastron, the belly armour, was also present. This is significant. Not all armoured animals protect their undersides as thoroughly as their tops. The presence of a plastron in Henodus means it was armoured from both directions, above and below, which speaks to the kind of threats it faced and the kind of environment it inhabited. In a shallow lagoon, a predator approaching from below is not impossible. Certain sharks and large fish attack from underneath. The plastron also would have helped when the animal rested directly on the substrate, providing a hard surface that protected the soft belly from rough sediment, sharp shell fragments, and anything lurking in the mud. The skull was small relative to the body. This is something you notice immediately in reconstructions and photographs of the fossil. The head seems almost disproportionately modest. tucked at the front of this wide, imposing shell like an afterthought. It was flat and wide rather than tall and narrow, which fits the general body plan. A tall skull would have added unnecessary height to an animal whose survival strategy was built around staying low. The eyes were positioned on the sides of the skull, giving a wide field of view, useful for an animal that needed to watch for threats from multiple directions simultaneously. The snout was short and broad, suited to a jaw that worked more like a beak than a set of teeth. The limbs were paddle-like, not as fully modified as the flippers of a sea turtle or the paddles of a plesiosaur, but clearly adapted for an aquatic life rather than efficient terrestrial locomotion. The bones of the limbs were somewhat shortened and flattened compared to a fully terrestrial animal, and the overall shape suggests they were used for slow, deliberate movement through shallow water rather than powerful swimming in open water. Think of the way a large freshwater turtle moves through a river, not fast, not graceful, but purposeful and controlled. The limbs of Henodus would have worked in a broadly similar way, pushing water and providing gentle propulsion and steering, while the animal moved along or just above the bottom. The tail was short. This is another departure from the typical body plan of an active swimmer. Many aquatic animals use the tail as a primary source of propulsion, sweeping it side to side to generate thrust. A short tail does not generate much thrust. Henodus was not built for speed in any direction. The short tail, combined with the paddle limbs and the wide, heavy shell, all point consistently toward the same conclusion. This was an animal that moved slowly and did not need to move quickly. Whatever it was doing in that Triassic lagoon, it was not chasing prey at speed. It was not fleeing predators at speed. It was doing something else entirely, something that rewarded patience and endurance over agility. When you put all of these features together and try to construct a mental image of the living animal, what you get is something genuinely striking in its strangeness. Picture a large, flat, roughly square shape resting on the bottom of a shallow, warm sea, the surface of its back covered in a mosaic of interlocking bony tiles. A small flat head extending from one end, 4 stubby paddle-like limbs extending from the sides, a short thick tail at the back. The overall profile, seen from the side, would have been very low, almost like a stone or a piece of reef. From above, the square outline and tiled surface would have given it a geometric quality, almost architectural, like something built rather than grown. The colour is unknown, of course, no soft tissue preserved. But it is worth thinking about. Many bottom-dwelling animals are coloured to blend with the substrate, browns and greys and muted patterns that make them difficult to spot against sand or mud or algae-covered rock. It is entirely plausible that Henodus was similarly camouflaged, its tiled shell blending with the patchy, irregular bottom of the lagoon. An animal that cannot move quickly to escape predators has strong incentive to be difficult to see in the first place. The weight of all that bone would have been considerable. This is not a trivial point. The osteoderm mosaic, the plastron, the dense skull, the shortened but still substantial limb bones, all of this added up to a skeleton that was heavy in proportion to the animal's size. In water, that weight is partially offset by buoyancy, but Henodus would still have been negatively buoyant, meaning it tended to sink rather than float. For a bottom-dwelling animal, this is actually useful. You do not need to expend energy to stay on the bottom. You simply rest there, and the weight keeps you in place. The effort goes into rising, not into sinking. It is an elegant solution, in a quiet sort of way. A body designed to belong to the floor of the sea. There is something almost architectural about the whole design, as though the animal were built to specifications rather than evolved through the usual messy process of trial and error. Of course it was evolved, and the process was neither quick nor neat. But the end result has a kind of internal logic that feels almost deliberate. Every feature reinforces the others. The wide shell provides stability and defense. The low profile reduces the target presented to predators. The paddle limbs allow slow movement without requiring the animal to sacrifice the heavy build that makes it defensible. The plastron protects the underside. The short tail reduces drag without compromising the overall plan. Even the small skull, seemingly modest and almost understated, fits perfectly into the low, flat silhouette. This is what makes Henodus so interesting to look at, even in fossil form. It is not a transitional animal, not something caught between two body plans, not an awkward intermediate form. It is a finished thing, fully committed to its design. The mosaic was complete, the limbs were modified, the skull was shaped, the tail was reduced. There is nothing tentative about any of it, and yet, as noted at the end of the previous section, there is that one feature that disrupts the expected story, the teeth. Or rather, the near total absence of them. Because everything else about Henodus points toward a heavily defended, bottom-dwelling, slow-moving animal that was a committed member of the Placodont group, and the Placodonts were, by definition and by name, the plate-toothed animals. The group that specialised in crushing hard-shelled prey with broad, flat, pavement-like teeth. It was their defining characteristic, the thing that gave them their ecological identity in the Triassic seas. Henodus had almost none of that. A single small tooth on each side of the jaw, lateral in position, modest in size. The rest of the jaw was a wide, flat, keratinous beak. And this raises a question that the physical description alone cannot answer. Because the body tells us where Henodus lived, and how it defended itself and how it moved. But the jaw tells us something else, something about what this animal was actually doing with its time, what it was eating, how it was finding food, and why it had abandoned the very feature that defined its entire evolutionary group. That question, the feeding question, is where the physical description leads us now, directly and unavoidably. The skull is small and flat and wide, the jaw is broad and beak-like, the teeth are almost gone, and the animal is sitting in a warm, shallow, hypersaline lagoon at the edge of the Triassic world. What was it eating? How was it eating? And what does the near-toothless jaw tell us about a life that, in every other respect, seemed so thoroughly and carefully designed? So let us start with the name itself, because it is actually a useful place to begin. Henodus. The name was given by Friedrich von Huene in 1936, and it means, roughly, single-toothed. He saw the jaw, he counted what was there, and he named the animal accordingly. That name has held for nearly 90 years now, and every time someone reads it, it raises the same question it raised in 1936. Why would a placodont, an animal from a group defined by its teeth, have almost none? To understand how strange this is, it helps to spend a moment with what the other placidonts were doing with their mouths. Take Placodus, one of the earlier and better-known members of the group, living around 245 million years ago. Placodus had teeth that looked almost like cobblestones set into the jaw, broad, flat, rounded and immensely strong. The front teeth were slightly more peg-like, used for prying shellfish off surfaces. The back teeth were the crushing apparatus designed to take a clam or a mussel, or a thick-shelled invertebrate and reduce it to fragments with a single bite. The force involved would have been considerable. Biomechanical estimates for similar toothed animals suggest jaw pressures that could crack through shell material that would defeat a human hand without any difficulty at all. The whole skull of Placodus was built around this function, robust and reinforced, with large muscle attachment areas and a deep jaw structure to support the load. That was the placodont identity. Slow animals with powerful jaws, moving along the seafloor, crunching through the hard-shelled things that other animals could not easily eat. It was a successful strategy, at least for a while, and it shaped the whole group's anatomy, their skulls, their teeth, their jaw muscles, the depth of their snouts. Henodus had abandoned almost all of it. What remained was a single small tooth on each side of the upper jaw, positioned toward the back and to the side, not in the crushing position of the classic placodont arrangement. Small, unremarkable, not obviously designed for breaking through anything substantial. And then, extending from the front and sides of the jaw, a wide, flat, keratinous beak. Keratin is the same material as a bird's beak, a turtle's beak, a tortoiseshell, a fingernail. It is hard, it is durable, it can be shaped by growth into quite precise forms, but it does not fossilise. What we know about the beak of Henodus comes from the bone underneath, the shape of the jaw margins, the texture of the bone surface, the way the edges of the jaw are formed. When bone underlies a keratinous structure in a living animal, it tends to show particular surface textures, small pits and grooves and ridges that are different from exposed bone. The jaw of Henodus shows exactly these features. So while no one has ever seen the actual beak, the bone tells us it was there. The overall jaw shape was wide and somewhat rounded at the front, not pointed like a predator's snout, not narrow like something designed for precision, but broad and flat like a spatula or a shovel. The lower jaw matched the upper in width. When the mouth closed, the two flat surfaces would have come together along a wide, even contact, not a slicing bite, not a puncturing bite, but a pressing, clamping or scooping action. This is where the hypotheses begin, and where the honest answer is that nobody is entirely sure. The first and perhaps most frequently discussed possibility is filter feeding. This is the idea that Henodus was using its wide beak to take in water and sediment and then push the water back out through some kind of filtering structure, retaining small food items in the process. Filter feeding is used by a remarkable range of modern animals: whale sharks, manta rays, flamingos, baleen whales, certain species of fish. The common thread is a body or structure that allows large volumes of water or sediment to be processed while retaining small nutritious particles. The appeal of this hypothesis for Henodus is that it explains the reduction of teeth. If you're not biting or crushing anything, you do not need teeth. The beak provides the intake structure. The filtering happens through soft tissue that does not preserve, and the wide, flat jaw shape is consistent with a scooping or sweeping motion that could take in material from the bottom or from the water column. Some researchers have pointed to the shape of the jaw as particularly suggestive of a ray-like feeding style. Modern rays that feed on soft-bodied prey or on sediment often have wide, flat mouth structures that bear some resemblance to what we see in Henodus. The analogy is not perfect. Rays are cartilaginous fish and are not remotely related to placodonts, but the functional comparison is worth considering. If Henodus was sweeping its wide beak across the lagoon bottom, taking in mouthfuls of sediment-rich water and filtering out small crustaceans, worms or organic particles, that would explain a great deal about its anatomy. The beak provides the scoop. The lack of teeth removes the need for crushing. The wide jaw provides the surface area needed to process volume rather than individual prey items. The problem with the filter feeding hypothesis is that it is difficult to confirm from bone alone. Soft tissue does not preserve. The filtering apparatus, if it existed, was made of material that is gone. What we have is the jaw shape, the beak evidence, and the absence of teeth. These are consistent with filter feeding, but they are also consistent with other possibilities. Consistency is not proof. The second hypothesis is that Henodus was eating soft-bodied prey, things without shells, things that did not require crushing force to consume. Worms, soft invertebrates, perhaps jellyfish-like organisms, perhaps aquatic insect larvae, perhaps small fish. If the prey was soft enough, a keratinous beak could handle it without any teeth at all. Many modern animals eat soft prey with beaks and no teeth. Birds are the obvious example, though birds represent an enormous range of dietary strategies, and not all of them are helpful comparisons. The point is that a beak is not inherently a filter-feeding tool. It can also be a gripping, tearing, or pressing tool for soft material. This hypothesis has a certain simplicity to it. Henodus lived in a shallow, warm lagoon that was likely rich in invertebrate life of various kinds. Worms and soft-bodied organisms are abundant in such environments, often more abundant than shelled prey, and they require far less jaw power to eat. If Henodus had shifted its diet toward these easier targets, the reduction of teeth would make sense. You do not need a crushing apparatus if nothing you eat requires crushing. The third possibility, and arguably the most surprising, is that Henodus was eating plant material. Aquatic vegetation. Algae perhaps, or the kind of microbial mats and aquatic plants that can carpet the bottom of shallow, nutrient-rich water bodies. This is the herbivory hypothesis, and it has been taken seriously by at least some researchers, partly because the jaw mechanics of Henodus are not inconsistent with it. A wide, flat beak that comes together along a broad surface can crop plant material effectively. Turtles, which are the obvious comparison, include many herbivorous species that use exactly this kind of beak to crop seagrass, algae, and other aquatic vegetation. The parallel is difficult to ignore. If Henodus was herbivorous, or at least partly so, it would represent another remarkable convergence with turtles, not just in body form but in dietary strategy. The shell, the beak, the wide flat jaw, the bottom-dwelling lifestyle, the slow movement through shallow water. All of it pointing in the same direction, toward a turtle-like ecological role occupied by an animal that was not a turtle at all. It is worth pausing on this for a moment, because it is genuinely striking. The placodonts were defined by their teeth and their shellfish diet. Henodus, the most armoured and the most turtle-like of all of them, had essentially walked away from that defining characteristic. It kept the armour, it kept the flat body, it kept the paddle limbs, it kept the bottom-dwelling lifestyle, but it replaced the crushing teeth with a beak, and it apparently shifted toward a diet that had nothing to do with hard-shelled prey. That is a significant departure, and it happened within a lineage that was already well established in its identity. Why? That is harder to answer. One possibility is the environment itself. The hypersaline lagoon where Henodus lived was not a typical marine habitat. Highly saline water is stressful for many organisms, and the kinds of shelled invertebrates that other placodonts fed on may have been scarce or absent in such conditions. If the hard-shelled prey was not there, the crushing teeth became less useful. If the lagoon was rich in algae, microbial mats, or soft invertebrates instead, a shift in feeding strategy would have made sense. The beak may have been an adaptation to a food source that was actually available in that specific environment rather than a general evolutionary trend. This connects to something worth noting about the jaw mechanics in a bit more detail. The jaw of Henodus was not just wide and flat. It was also designed for a specific kind of motion. The jaw joint and the muscle attachment areas suggest that the primary movement was a simple up and down action, a pressing or clamping motion, without the side-to-side grinding that characterizes many herbivores, and without the rotational or lateral movement that some filter feeders use. This is interesting because it does not clearly favour any one of the three hypotheses over the others. A pressing motion works for filter feeding, for gripping soft prey, and for cropping plant material. The jaw mechanics, in other words, are permissive rather than decisive. They rule out crushing hard shells, which is clear enough. But they do not clearly point toward one specific alternative. The honest position, which is where most researchers currently sit, is that the feeding ecology of Henodus remains uncertain. The evidence is consistent with filter feeding, with soft-bodied prey consumption, and with herbivory. It is possible that Henodus was doing more than one of these things, using its wide beak opportunistically across whatever food sources were available in its particular environment. Many animals are dietary generalists in practice, even when their anatomy seems to suggest specialization. And Henodus lived in a lagoon that was by any measure an unusual and somewhat unpredictable place. What is clear is that the jaw represents a genuine evolutionary break from the rest of the placodont group. Not a gradual shift, not a partial reduction, but a near total replacement of the ancestral dentition with something structurally and functionally different. One small tooth per side, and then a beak. The placodont crushing apparatus, which had been refined over tens of millions of years across multiple lineages, was essentially gone. Whether this was driven by the specific environment Henodus occupied, by a dietary shift towards softer or more plant-like food, or by some combination of pressures that we cannot fully reconstruct, The result was an animal that had redefined its relationship with food in a way that no other plastodont had done. There is a quiet irony in this, or perhaps something closer to a puzzle. The most armoured plastodont, the one that had taken the group's defensive strategy to its logical extreme, was also the one that had most thoroughly abandoned the group's feeding strategy. The shell said plastodont. The jaw said something else entirely. And trying to reconcile those two facts is part of what makes Henodus such an interesting fossil to spend time with. It is not a simple animal. It is not a straightforward case study. It is a creature that, even in death, even as a piece of compressed limestone in a museum drawer, keeps asking questions that do not have easy answers. The jaw and the feeding question also connect directly to where Henodus lived, because the diet of an animal is inseparable from its environment. What was available in that lagoon, what the water conditions were like, what grew on the bottom and what swam through the shallows, all of these things shaped what Henodus could eat and how it went about finding food. And the environment of Henodus was itself unusual, perhaps even extreme, in ways that help explain not just the feeding mystery but several other aspects of this animal's peculiar existence. So let us spend some time in that environment, because it shapes everything else about this animal, and it is itself a strange and rather extreme place. The world of the Late Triassic was profoundly different from the one we know. There was no polar ice. The planet was warmer across the board, and sea levels were configured in ways that would be unrecognisable today. The great supercontinent of Pangaea was still in the process of breaking apart slowly over millions of years, and the ocean that filled the widening gaps between its pieces was the Tethys Sea. The Tethys was vast. At its widest, it stretched from what is now the Western Mediterranean region, all the way east through the Middle East and into Central Asia. It was a warm, shallow, tropical ocean for much of its history, surrounded by low-lying land and broken up along its margins by bays, inlets, archipelagos and coastal flats. It was not a single uniform body of water, but a complex patchwork of different marine environments, some open and deep, others shallow and warm, and cut off from the main circulation. Henodus did not live in the open Tethys. It lived on the western edge of that ocean, in a specific kind of coastal environment that was far more restricted and far more chemically extreme than the open sea. The formation where it was found, the Gypscupa, is a geological unit deposited in the Late Triassic across parts of what is now southern Germany and neighbouring regions. The name itself is a clue. Gyps is the German word for gypsum, and gypsum is a mineral that tells a very specific story about the water it formed in. Gypsum does not precipitate out of ordinary seawater under normal conditions. It forms when water evaporates significantly, concentrating the dissolved salts until they begin to crystallize out. The presence of thick gypsum layers in the Gypscupa tells geologists that the water in this environment was evaporating faster than it was being replenished. The lagoons and shallow basins of the western Tethys margin were at times becoming hypersaline, saltier than the open ocean, saltier, in some intervals, than most marine organisms can tolerate. This is not a gentle place. Hypersaline environments are biologically stressful. The osmotic pressure that high salt concentrations place on living cells is significant. Many organisms that thrive in normal marine conditions cannot survive in hypersaline water. Fish become scarce. Diverse invertebrate communities thin out. The kinds of predators that patrol normal coastal seas, large fish, active marine reptiles, mobile hunters, tend to avoid these environments because the prey base is too sparse and the physiological cost is too high. What remains in hypersaline lagoons tends to be a simplified community. Microbial mats, salt-tolerant algae, certain brine-adapted invertebrates, organisms that can cope with conditions that exclude everything else. In some ways, this is a refuge, a place where the usual rules of predator and prey are suspended, not because predators have been defeated, but because they simply cannot function there. An animal that could tolerate the hypersaline conditions would find itself in an environment with very few threats. And an animal that was slow, heavily armoured, and low energy in its lifestyle would be well suited to a place where food was sparse, but predators were also largely absent. This is one of the more compelling interpretations of why Henodus ended up in the Gipscupa. Not because hypersaline lagoons were ideal habitats in some absolute sense, but because they offered a kind of ecological shelter. The very harshness of the environment was a form of protection. If you could survive there, you were relatively safe from the things that might otherwise eat you, and Henodus, with its heavy armour and its wide flat body and its presumably slow metabolism, may have been well positioned to make that trade-off. The shell provided physical protection, yes, but living in an environment that most predators avoided provided a different kind of protection, one that came from geography rather than biology. Both strategies working together would have made Henodus quite difficult to prey upon, even without being fast or agile or particularly alert. The gypsum deposits in the Gipscupa are not continuous. They are interbedded with other sediments, including limestone and mudstone, which suggests that the conditions in these lagoons fluctuated. There were periods of more normal marine influence, when water from the open tethys refreshed the lagoons and salinity dropped. Then there were periods of increased evaporation, when the lagoons became more isolated, saltier and harsher. Henodus lived through these fluctuations, or at least its ancestors did over many generations. The animal's physiology must have been tolerant of a fairly wide range of conditions, or at least capable of moving between areas of different salinity as conditions shifted. The temperature of this environment would have been warm. The Late Triassic was a greenhouse world, and the western tethys margins at low to mid latitudes would have experienced warm water temperatures year-round. There was no cold season in the way we experience it. The shallow lagoons would have been particularly warm, since shallow water heats up faster than deep water, and the evaporation that concentrated the salts also concentrated the heat in some sense. This was a warm, bright, salty, shallow world. Not lush, not biologically rich in the way a coral reef is rich, but functional in its own stripped-down way. The oxygen content of the water is another consideration. Hypersaline and warm water holds less dissolved oxygen than cool, well-circulated water. At the bottom of a shallow, stagnant lagoon in a warm climate, oxygen levels could have been quite low at times. This is actually consistent with good fossil preservation, because low oxygen conditions at the seafloor slow down the decomposition of organic material. The fine-grained limestone of the Gipscupa, the kind that preserved Henodus in such remarkable detail, is itself partly a product of these quiet, low-energy, low-oxygen bottom conditions. The same environment that made life difficult is also the one that preserved the evidence of life so well. There is something almost poetic about that, though perhaps not the most comforting kind of poetry. What the bottom of this lagoon would have looked like is something we can reconstruct in broad strokes. Microbial mats are well documented in Triassic hypersaline environments. These are dense layered communities of bacteria and other microorganisms that form visible structures on the seafloor, sometimes soft and slimy, sometimes building up into low mounds called stromatolites. They are ancient communities, among the oldest forms of life on Earth, and they tend to thrive in conditions where more complex organisms struggle. In a hypersaline lagoon, microbial mats would have been a dominant feature of the bottom landscape. Algae, both attached and free-floating, would have been present during better oxygenated periods. Small invertebrates, the kinds that can tolerate high salinity, would have moved through the sediment or rested on the mat surface. This is the world Henodus moved through, slowly, close to the bottom, its wide, flat body hovering just above the sediment, its small head scanning whatever was in front of it. The light in a shallow tropical lagoon would have been strong, filtered through clear, warm water, illuminating the pale bottom with shifting patterns. The water would have been still much of the time, protected from open ocean waves by whatever barriers separated the lagoon from the main tethys. occasionally disturbed by wind or by the movement of the animals themselves, but generally quiet. It is worth noting that Henodus is the only large vertebrate known from the Gipscooper Formation in any abundance. This is consistent with the hypersaline interpretation. If the environment was too harsh for most marine vertebrates, Henodus would have been something of a specialist, the one large animal that had found a way to make this place work. Whether it was truly alone, or whether other large animals occasionally moved through the area during periods of lower salinity, is harder to say. The fossil record of the Gipscooper is not exhaustive. Absence of evidence is not the same as evidence of absence, as paleontologists are always careful to point out. Elsewhere in the broader Tethys region, during this same general period, other placodonts were present. Siamodontoids, the armoured group to which Henodus belonged, have been found in Triassic deposits across what is now Switzerland, Italy, Israel, and other parts of the ancient Tethys margin. Some of these were living in more normal marine conditions. Nothosaurs, the long-necked marine reptiles that were among the dominant predators of the Triassic seas, were common in the open Tethys and its less extreme coastal waters. Early ichthyosaurs were present in deeper water settings. The Triassic Ocean was not empty. It was recovering from the Permian extinction, still rebuilding its ecosystems, but active and increasingly complex. Henodus, by retreating into the hypersaline lagoons, had essentially stepped out of that broader marine world. It had found a corner of the environment that was too difficult for most of its contemporaries and settled there. Whether this was an active ecological strategy in any meaningful sense, or simply the result of evolutionary pressures that gradually pushed the lineage toward more extreme environments, is impossible to say. Evolution does not make deliberate choices, but the outcome is clear enough. Henodus ended up in a place that was unusual, restricted, and in many ways defined by its harshness, and it appears to have been well adapted to that place. The connection between the environment and the feeding mystery, which we spent time with in the last section, becomes clearer here. If the Gipscooper lagoons were too saline for the dense populations of hard-shelled mollusks and crustaceans that other placodonts fed on, then the ancestral placodont feeding strategy would have been of limited use. The crushing teeth, the powerful jaw musculature, the whole apparatus built for processing shellfish would have had little to work with. What was available was microbial mat, algae, soft-bodied invertebrates, and perhaps small fish during periods when salinity dropped enough to allow them in. A wide, flat beak, capable of cropping or scooping or filtering, would have been far more useful in this context than a set of heavy crushing teeth. This does not prove that the environment drove the dietary shift. It is possible that the shift happened first, and that Henodus's changed feeding strategy allowed it to colonize these marginal environments. Cause and effect in evolutionary history are often genuinely difficult to untangle, but the fit between the animal and the environment is striking. The beak, the armour, the flat body, the heavy bones, the slow lifestyle, all of these traits make more sense together when you place them in the context of a warm, shallow, hypersaline lagoon with few predators, sparse food, and quiet water. There is also the question of whether Henodus spent any time out of the water. The Gipscooper deposits include evidence of periodic exposure, times when the lagoon shallowed enough that the bottom was at or near the water surface, salt flats, mud flats, evaporate crusts. An animal living in a lagoon that occasionally dried down or became so shallow that it was essentially a mud flat would have needed some ability to cope with temporary terrestrial conditions. Whether Henodus could haul itself onto land, even briefly, is a question we will come back to when we look more carefully at its limbs and locomotion. But the environment itself raises the possibility. A lagoon that sometimes becomes a mudflat is a lagoon that rewards the ability to move at least a short distance on land. What the Gipscooper environment ultimately gives us is a context for understanding Henodus, not just as a strange-looking fossil, but as a functioning animal with a specific ecological strategy. It was not simply a creature that happened to look like a turtle. It was an animal that had found a particular kind of place in the world, a stressed, marginal, hypersaline lagoon on the edge of an ancient sea and had shaped itself over millions of years of evolution into something that could live there. The armour, the beak, the flat body, the slow movement, the tolerance for harsh conditions, all of it fits together when you see the environment clearly. And the environment itself raises a further question. If Henodus was well adapted to this specific place, if it had essentially built its entire existence around the conditions of the Gipscooper lagoons, then how did it actually move through that world? How did it navigate the shallow water, the muddy bottom, the occasional dry periods? The body plan tells part of the story, but the limbs and the mechanics of movement tell another, and that part of the picture is worth looking at carefully. So we have a picture of the environment now, and we have a picture of the animal inside it. What we have not yet done is populate the world around Henodus, to look at what else was living in and near that lagoon, and what kind of ecological position this flat, armoured, slow-moving creature actually occupied. Because even a stressed marginal environment is not an empty one. Life finds its way into difficult places, and the Gipscooper lagoons, harsh as they were not lifeless. The fossil record from the Gipscooper Formation itself is not particularly rich in terms of large vertebrates, but it does contain smaller organisms. Fish remains have been found, though they are fragmentary. Small invertebrates, the kinds of creatures that can tolerate fluctuating salinity, were almost certainly present. Bivalves and gastropods, some adapted to brackish or hypersaline conditions, have been recovered from Triassic evaporate environments similar to the Gipscooper. Microbial mats, the dense carpets of photosynthetic bacteria that thrive in warm, shallow, high salinity water, would have been a persistent feature of the lagoon floor. These mats are tough, chemically complex and not particularly nutritious, but they represent a biological baseline, a layer of organic material coating the substrate, and in a sparse environment, even that baseline matters. The picture that emerges is of a lagoon that was alive, but quietly so. Not the rich, diverse reef community of a healthier marine environment, but a simplified ecosystem, dominated by microbes and small invertebrates, with very few large animals present. In ecological terms, this is sometimes called a stressed community. The diversity is low, the biomass is concentrated in a few tolerant species, and the energy pathways are relatively simple. For an animal like Henodus, this kind of environment had a specific implication. There was food, but it required a particular approach to find and process it, and there were few competitors for whatever food existed, because few animals could survive there at all. It is worth thinking about what Henodus's daily existence might have looked like in practical terms, not in a fanciful way, but in the way a biologist might think about it, based on what the body plan and the environment together suggest. Henodus was probably slow. The heavy shell, the dense bones, the paddle limbs, none of these are the anatomy of a fast animal. It was likely moving across the bottom of a shallow lagoon, somewhere between a few centimetres and perhaps a metre or two of water depth at most, dragging or pushing itself along with its limbs, its flat belly close to the substrate. The wide, flat beak would have been in contact with the bottom, or very close to it, as the animal moved. Whatever it was eating, it was probably finding it on or just above the lagoon floor. Modern analogies are imperfect, but they are useful for building a mental image. A large horseshoe crab moving through shallow water, turning over sediment with its body as it goes, is one kind of comparison. A sea turtle grazing on seagrass, moving slowly and methodically, is another. A bottom-feeding ray, pressing its flat body against the substrate and using its mouth to process whatever is beneath it, is perhaps closest in terms of the physical interaction with the environment. None of these are exact parallels. Henodus was not a ray, not a turtle, not a horseshoe crab. But the lifestyle it seems to have led has echoes in all of them. The question of what else was sharing the broader Tethys region during this period is worth addressing, even if those animals were not necessarily in the lagoon with Henodus on a daily basis. The Late Triassic Tethys was, in the open marine sections, a reasonably active and diverse environment. Nothosaurs were among the most significant predators. The These were long-necked reptiles, some reaching several meters in length, with sharp teeth designed for catching fish. They were not built for shallow hypersaline lagoons, but they were present in the coastal and nearshore waters of the Tethys, and during periods when salinity in the Gipscooper lagoons dropped, it is possible that nothosaurs could have moved into the shallower margins. Whether they posed any real threat to Henodus is uncertain. A fully armoured Henodus, flat on the bottom, would have presented a very difficult target for a predator whose strategy was built around catching fast-moving fish. The armour was not decorative. Other Yamadontoid placodonts were living in the broader Tethys region at roughly the same time. Henodus, one of the better-known armoured placodonts, has been found in Triassic deposits from Switzerland and Germany, in sediments that suggest somewhat less extreme marine conditions than the Gipscooper. Cephaderma, another Yamadontoid, is known from slightly later deposits in the Alps. These animals were broadly similar to Henodus in their armoured body plan, though they differed in the details of their shell structure and skull anatomy. The fact that multiple armoured plecodonts were living in overlapping geographic regions during the Triassic suggests that the Yamadontoid lineage was, for a time, genuinely successful. The armoured body plan was not a dead end. It was a working strategy, replicated across several related lineages in slightly different forms. Early ichthyosaurs were also present in the Triassic Tethys, particularly in deeper water settings. These were the fish-shaped marine reptiles that would go on to dominate the Jurassic oceans, and in the Triassic they were already diverse and widespread. Animals like Mixosaurus, a relatively small ichthyosaur known from Triassic deposits across Europe and Asia, were active swimmers in the open water. They would not have been regular visitors to the hypersaline lagoons where Henodus lived, but they were part of the broader marine world that surrounded those lagoons. On land, not far from the shores of the Tethys, the world was undergoing its own extraordinary transformation. The Late Triassic was the period when dinosaurs first appeared. Early dinosaurs like Eoraptor and Herrerasaurus were present in South America by around 231 million years ago, and by the time Henodus was alive in its German lagoon, dinosaurs were beginning to spread across the supercontinent Pangaea. These early dinosaurs were mostly small, bipedal, and not yet the dominant animals they would become. The large terrestrial ecosystem of the Triassic was still controlled by other groups, including etosaurs, large armoured herbivores, and Rauisuchians, powerful predatory archosaurs. But the dinosaurs were there, beginning their long climb toward dominance. This temporal coincidence is one of the things that makes the Late Triassic such a fascinating period. Henodus, lying on the bottom of its lagoon in what is now southern Germany, was alive at the same time as the earliest dinosaurs. The two groups never interacted in any meaningful way. One was a secondarily aquatic reptile retreating into a marginal marine environment. The others were terrestrial animals just beginning to establish themselves on land. But they were contemporaries, separated by the shoreline, by ecology, by evolutionary history. The Triassic was a period of extraordinary biological experimentation, and Henodus was one of its more unusual products. The Permian extinction context is also relevant here. The Great Dying as the end, Permian extinction is sometimes called, occurred around 252 million years ago, roughly 22 million years before Henodus lived. It was the most severe mass extinction in Earth's history, eliminating somewhere between 90 and 96% of all marine species. The recovery from that event was slow and uneven. For much of the early and middle Triassic, marine ecosystems were simplified and stressed, not entirely unlike the hypersaline lagoon environment that Henodus inhabited much later. By the Late Triassic, ecosystems had recovered considerably, but the recovery was not uniform. Some environments were rich and diverse. Others, particularly the marginal and stressed environments like hypersaline lagoons, remained ecologically simplified. In a sense, Henodus was living in an environment that resembled, in some ways, the post-extinction world of the early Triassic. Not because the global ocean was still recovering, but because the specific lagoon environment was itself a kind of permanent stress zone. The conditions that made it inhospitable to most animals also made it a refuge of sorts for the animals that could tolerate it. This is a pattern that appears repeatedly in ecological history. Stressed environments, whether they are hypersaline lagoons, acidic peat bogs, or hydrothermal vents, tend to have low diversity but can support highly specialised animals in significant numbers, precisely because competition and predation are reduced. Whether Henodus lived in large numbers or in small scattered populations is something the fossil record cannot tell us directly. The single known specimen from the Gippscooper is not enough to draw population conclusions, but the environment suggests that the lagoon could have supported a modest population of animals with Henodus's lifestyle, provided the food supply was adequate and the salinity did not fluctuate beyond the animal's tolerance range. There is one more element of the ecosystem picture worth considering, and it connects back to the feeding question in an interesting way. Microbial mats, which were almost certainly present in the Gippscooper lagoons, are not just passive floor coverings. They are chemically active communities. They produce oxygen through photosynthesis during the day, but they also consume oxygen at night. And in warm, shallow, enclosed water, this daily cycle can cause significant fluctuations in dissolved oxygen levels. During the day, the water above a microbial mat can be supersaturated with oxygen. At night, oxygen levels can drop sharply. Animals that live in close association with microbial mats need to be able to tolerate these fluctuations, or they need behavioural strategies for managing them, such as moving to slightly deeper or better oxygenated water at night. Whether Henodus had any behavioural flexibility of this kind is unknown, but the heavy, dense skeleton and the armoured body suggest an animal that was not making rapid or long-distance movements. If oxygen levels in the lagoon dropped at night, Henodus's response was probably not to swim quickly to a better location. It was more likely to simply tolerate the conditions, as many bottom-dwelling animals do, relying on physiological tolerance rather than behavioural escape. This is consistent with the general picture of Henodus as a slow, low-energy animal, adapted to making the most of a difficult environment, rather than actively managing its position within it. The food web of the Gippscooper lagoon, as best as we can reconstruct it, was simple. Sunlight drove microbial mat production. Small invertebrates grazed on the mats or on organic particles in the water. Henodus processed whatever the lagoon floor offered, whether that was algae, microbial mat material, soft invertebrates, or some combination of all three. There were few, if any, large predators. The energy flow was shallow and linear, not the complex layered web of a diverse marine ecosystem. Henodus sat near the top of this simple food web, not because it was powerful or fast, but because it was the largest animal present, and because its armour and low-profile lifestyle made it effectively invulnerable to whatever predation pressure existed. This is a quieter kind of ecological success than we usually celebrate. It is not the success of the apex predator, swift and dominant. It is the success of the specialist, the animal that found a place no one else wanted and made it work. There is something almost admirable about that, in a quiet way. Henodus did not conquer its environment. It accommodated itself to it, shaped itself around its limitations, and persisted. For somewhere between 2 and 5 million years, based on the stratigraphic range of the Gippscooper Formation, this flat, armoured, slow-moving animal went about its business in its warm, salty lagoon, doing whatever it was doing with that wide, flat beak, moving slowly across the bottom, probably not in any particular hurry. And then, eventually, the question of how it moved through that world becomes impossible to avoid. The ecosystem picture places Henodus in its environment, but the body mechanics tell us how it actually navigated that environment, how it got from one place to another, how it managed the transition between water and the occasional exposed mudflat, and what the physical experience of being Henodus might have looked like in motion. The limbs, the bone density, the shell weight, the paddle morphology, All of these come together in the locomotion question, and that question turns out to be more complicated than it might first appear. So let's think about the limbs for a moment, because the limbs are where the locomotion question really begins, and they're also where it gets complicated in ways that are easy to miss if you only look at the overall shape of the animal. Henodus had 4 limbs. That much is clear from the fossil. What is also clear is that those limbs were modified in a way that suggests a predominantly aquatic lifestyle. The bones of the forelimbs and hind limbs were shortened and broadened compared to a typical terrestrial reptile. The individual digits, the bones that would correspond to our fingers and toes, were arranged in a way that would have made the limb function more like a paddle than a foot. Not a highly refined paddle, like the long, elegant flipper of a plesiosaur, but something closer to a broad, flat surface that could push through water with reasonable efficiency. Think of it less like a fish's fin, and more like a wide, flat hand held open and pressed sideways through water. Functional, but not especially hydrodynamic. This is an important distinction. Plesiosaurs, which were living in the broader Tethys Sea at roughly the same time, had evolved limbs that were fully committed to aquatic locomotion. Their flippers were long, narrow, and highly specialised, built around elongated digit bones that gave the limb a wing-like shape. They were underwater flyers in a sense, using their flippers to generate lift and thrust through the water column the way a bird uses its wings through air. Henodus was not doing that. The limbs were modified, yes, but they had not gone all the way down the road toward full aquatic specialisation. There was still enough structure in those limbs to suggest that Henodus retained at least some capacity for movement on a solid surface. This is where the amphibious hypothesis comes in, and it is one of the more interesting unresolved questions about this animal. Some researchers have proposed that Henodus was not a fully aquatic animal, but rather a semi-aquatic one, capable of hauling itself out of the water onto mudflats, shallow banks or salt flats, in much the same way that a modern sea turtle or a large freshwater turtle will occasionally move onto land. The comparison to a modern snapping turtle is actually a useful one here. Snapping turtles are not graceful on land. They are slow, awkward, and clearly more comfortable in water. But they can move on land when they need to, and they do so with a kind of determined, lumbering persistence that gets them where they are going eventually. Henodus may have moved in a broadly similar way, at least on the occasions when it was out of the water. Whether it went onto land regularly or only occasionally is something we cannot determine from the fossil alone. The limb morphology is suggestive but not conclusive. What we can say is that the limbs were not so fully modified as to make land movement impossible, and the environment Henodus lived in would have provided plenty of opportunities for land excursions. The hypersaline lagoons of the Gipskoiper were shallow and surrounded by exposed salt flats and mud flats, especially during the drier seasons when evaporation would have lowered water levels. An animal that could move onto these exposed surfaces even briefly would have had access to areas that a fully aquatic animal could not reach. Whether that represented a meaningful ecological advantage for Henodus specifically is harder to say, given the uncertainty about its diet. There is also the question of what movement on land would have actually looked like mechanically. The shell creates a significant constraint. A wide, flat carapace like the one Henodus carried would have distributed weight broadly across the body, which is good for buoyancy management but creates challenges for walking. The limbs would have had to extend outward from beneath the shell and then push downward and backward to generate forward movement. This is essentially the same basic mechanics as a turtle, and turtles manage it well enough, though not quickly. The gait would have been a slow, wide-legged shuffle, with the body low to the ground and the shell providing a kind of stabilising weight that kept the animal from tipping. It would not have been elegant, but it would have worked. In water, the picture is somewhat different, and in some ways more interesting. Henodus in water was not fighting its shell the way it would have been on land. The water would have provided buoyancy, reducing the effective weight of the armour significantly. But this raises its own question, because all that bone is dense, and dense bone tends to make an animal negatively buoyant, meaning it sinks rather than floats. For many aquatic animals, negative buoyancy is a problem. For a bottom dweller, it is actually an advantage. This is something worth pausing on, because it is counterintuitive at first. We tend to think of buoyancy as something an aquatic animal wants to have. Dolphins and sea turtles manage their buoyancy carefully, using air in their lungs to stay at a comfortable depth without constant effort. But an animal that lives on or near the bottom of a shallow body of water does not necessarily want to float. An animal that sinks naturally can rest on the bottom without effort, can stay in place without fighting a current, and can move along the bottom without having to actively push itself downward. The heavy, dense skeleton of Henodus, combined with the weight of the shell, would have made it naturally inclined to stay low in the water column. In a shallow lagoon with a soft sediment floor, this is exactly where you want to be if you are feeding on bottom-associated food sources. Modern analogues for this kind of lifestyle are not hard to find. Horseshoe crabs are negatively buoyant and spend most of their time on or near the sea floor. Many species of flatfish are negatively buoyant and rest on the bottom between feeding bouts. Some rays and skates are bottom-associated in a similar way, using their flat bodies and dense skeletons to stay low without constant muscular effort. Henodus, in its own Triassic way, was probably doing something broadly similar, resting on the bottom, moving slowly when it needed to, expending as little energy as possible in an environment where food was not necessarily abundant. The actual mechanics of swimming, when Henodus did swim, would have involved a combination of limb paddling and body movement. The limbs would have provided most of the propulsive force, sweeping backward and outward in a motion that pushed water behind the animal and moved it forward. The body itself, being relatively inflexible under all that armour, probably contributed less to propulsion than in a more flexible swimmer. The tail was short and not particularly muscular looking in the reconstructions, so it likely contributed little in the way of propulsive force. The overall impression is of an animal that moved through water slowly and steadily, not in bursts, not with sudden changes of direction, just a patient, low-energy progression across the lagoon floor or through the shallow water column above it. There is a question about how Henodus managed transitions between different depths within the lagoon. The Gipskupur lagoons were shallow overall, but shallow does not mean uniform. There would have been areas of slightly deeper water, channels, depressions in the sediment floor, and areas of very shallow water near the margins where the lagoon met the exposed salt flats. Moving between these different microenvironments would have required some flexibility and locomotion, even if the overall movement pattern was slow. An animal that could only function in one narrow depth range would have been at a disadvantage compared to one that could move fluidly between slightly deeper water and the very shallow margins. The paddle limb suggests that Henodus was capable of this kind of flexibility. In deeper water, the limbs could work as paddles, generating forward motion through the water. In very shallow water, the same limbs could function more like legs, pushing against the soft sediment floor and propelling the animal forward in a walking or punting motion. This dual-use capability, limbs that work both as paddles and as legs, is actually common in semi-aquatic animals. River otters do something similar. So do platypuses, in their own odd way. The limb does not need to be perfectly optimized for either function to be useful in both. It just needs to be functional enough in each context to get the job done. What we cannot know from the fossil is the quality of Henodus' sensory experience of its environment. How well did it see? Did it use smell or taste to locate food? Did it have any sensitivity to vibrations in the water, the way many modern aquatic animals do? The skull is preserved, but the soft tissues of the sensory organs are long gone. We can infer from the skull shape that the eyes were positioned in a way consistent with moderate lateral vision, but detailed reconstruction of the visual field is not possible from the material available. The brain endocast, the impression left by the brain inside the skull, could in principle tell us something about which sensory systems were most developed, but detailed endocranial studies of Henodus are limited by the state of preservation of the single known specimen. What we are left with, then, is a composite picture built from inference and analogy. A slow-moving, bottom-associated animal, probably semi-aquatic, capable of hauling onto exposed surfaces but most comfortable in shallow water, negatively buoyant, moving with patient, low-energy paddling strokes, spending much of its time at or near the lagoon floor. Not built for speed, not built for pursuit, not built for rapid escape, built instead for persistence, for the long, unhurried business of finding food in a difficult environment and processing it with a wide, flat beak that we still do not fully understand. There is something almost meditative about imagining Henodus in motion. Not the dramatic locomotion of a predator, not the explosive burst of a prey animal evading capture, just a slow, deliberate movement across the bottom of a warm, salty lagoon, the shell catching a little light from the surface above, the paddle limbs working in a steady rhythm, the wide skull angled slightly downward toward whatever the bottom had to offer, is not a glamorous image. But it is a real one, or as real as we can make it from the evidence available. The locomotion picture also connects back to the predator pressure question in an interesting way. An animal that moves slowly is, in most environments, vulnerable to predators. Speed is one of the primary defences available to prey animals, and Henodus clearly did not have it. The armour, then, was not supplementary protection for an otherwise fast or agile animal. It was the primary and perhaps only meaningful defence available. This reinforces the interpretation that the shell was not an incidental feature of Henodus's body plan, but a central one, the thing that made the slow, bottom-dwelling lifestyle viable in the first place. Without the armour, the slow movement through shallow water would have made Henodus an easy target for any predator that happened to enter the lagoon. With the armour, the same slow movement became effectively safe, because there was nothing in the Gipscooper lagoon capable of breaching that shell. This is the logic of the turtle body plan, and it is also the logic of Henodus, arrived at independently, through a completely different developmental route, in a completely different evolutionary lineage, millions of years before turtles became a significant presence in marine environments. The same problem, the same solution, the same result. Slow, armoured, bottom-dwelling, patient. It is one of the cleaner examples of convergent evolution you can find in the entire fossil record, and the locomotion picture is part of what makes it so clear. Not just the shell shape, not just the beak, but the whole lifestyle, the whole ecological strategy, arrived at twice by animals that had no common ancestor remotely close to the point of convergence. It is worth noting that the locomotion of Henodus also tells us something about the energy budget of the animal. A slow-moving, negatively buoyant, bottom-dwelling animal in a warm, enclosed lagoon does not need to maintain a high metabolic rate. The evidence from plecodont bone structure generally suggests a relatively slow-growing, low-metabolism lifestyle compared to more active marine reptiles. This is consistent with what the locomotion picture suggests. Henodus was probably not a metabolically active animal. It was not generating large amounts of body heat, not making rapid movements, not processing food quickly. It was in the metabolic sense running on a low setting. This is actually a sensible strategy for an environment where food availability may have been unpredictable, and energy expenditure needed to be kept in check. The low metabolism, slow locomotion, heavy armour combination that Henodus represents is, in evolutionary terms, a coherent package. Each element supports the others. The heavy armour requires slow movement, because speed is biomechanically expensive and the shell adds weight. The slow movement requires armour, because without it, a slow animal is vulnerable. The low metabolism supports the slow movement and makes the heavy armour energetically affordable. And the bottom-dwelling lagoon floor lifestyle supports all of it, because it places the animal in an environment where speed is not necessary, where predators are rare, and where the food, whatever it was available at low energy cost. It all fits together in a way that feels almost designed, though of course it was not. It was the product of millions of years of selection pressure, each small change reinforcing the others until the whole system cohered into the animal we find in the Tübingen limestone. And that coherence, that sense of a complete and self-consistent ecological strategy, is part of what makes Henodus so satisfying to think about even now. It is not a transitional form caught awkwardly between two lifestyles. It is not a failed experiment that left no descendants because it could not quite commit to anything. It is a fully realised animal, complete in its own terms, adapted to its own specific world with a thoroughness that took millions of years to achieve. The fact that it looks like a turtle is almost a distraction from the deeper story, which is the story of how evolution finds the same answers through different routes, and how a slow, armoured, flat-bodied animal in a warm, shallow lagoon turned out to be a very good idea indeed, no matter which lineage was doing the inventing. Which brings us naturally to the question of where Henodus sits within the broader story of its own lineage, and what the arc of placodont evolution actually looked like from beginning to end. Because Henodus was not the beginning of that story. It was in many ways the culmination of it, the most extreme expression of a trend that had been building for tens of millions of years. And understanding how that trend developed, and why it ended when it did, adds another layer to everything we have already seen. So let us go back to the beginning of the placodont story, not to Henodus, but to the animals that came before it, the ones that would eventually give rise to the armoured branch and, at its far end, to the strange, flat, turtle-like creature we have been following through this warm Triassic lagoon. The earliest placodonts appeared roughly 245 million years ago in the Middle Triassic. The world at that point was still recovering from the Permian extinction, the largest mass extinction in Earth's history, which had wiped out something close to 90% of all marine species just a few million years earlier. Ecosystems were still reassembling themselves. Niches were open. And into that recovering world, the placodonts emerged as something genuinely new. A lineage of marine reptiles built around a very specific ecological strategy, finding hard-shelled prey on the seafloor and crushing it. The best-known early placodont is Placidus, which lived around 245 to 235 million years ago, in the shallow seas of what is now Central Europe. Placidus looked nothing like Henodus. It was a robust, heavy-bodied animal, somewhat lizard-like in overall shape, with 4 strong limbs and a relatively long tail. Its most distinctive feature was its teeth. It had large, flat, pebble-like crushing teeth on both the upper and lower jaws, clearly designed for processing hard-shelled prey, mollusks, bivalves, brachiopods, the kinds of things that lived in abundance on Triassic sea floors. The teeth were not sharp. They were not designed for cutting or tearing. They were designed for pressing and cracking like a nutcracker built into the skull. Placodus also had a relatively robust skeleton, but it had no armour, no shell, no osteoderms, no bony plates embedded in the skin. It was in that sense a fairly unprotected animal, relying on its size and perhaps its habitat to avoid predators rather than on any physical defence. Placidus gives us the baseline. It shows us what the placodont body plan looked like before the armouring trend began, and it also shows us something important about the ecological niche the whole group was occupying: shallow coastal waters, bottom-feeding, hard prey, slow lifestyle. The foundation was already there. What came next was a series of modifications layered on top of that foundation, and those modifications moved in a very clear direction. The chiamodontoids were the armoured branch of placodonts, and they represent one of the most dramatic evolutionary trends in the entire Triassic marine world. The name refers to a group of placodonts that began developing bony armour, osteoderms embedded in the skin, forming a mosaic of protective plates over the back and eventually the belly. The earliest chiamodontoids had modest armour, scattered osteoderms that provided partial coverage. But as the group diversified through the Middle and Late Triassic, the armour became progressively more elaborate, more complete, and more structured. Different lineages within the chiamodontoids developed their armour in slightly different ways, which is itself a fascinating detail. The trend toward armour did not happen just once and then spread. It happened multiple times, independently within the broader Siamodontoid group. Different lineages arrived at similar solutions through their own separate paths. This is convergence within convergence, a smaller version of the larger pattern that makes Henodus so interesting in relation to turtles. Siamodus is one of the better-known intermediate forms. It lived roughly 240 to 235 million years ago, somewhat earlier than Henodus, and it had a more developed shell than Placodus but less complete coverage than Henodus. The carapace of Chiamodus was clearly turtle-like in outline, but the individual elements were larger and less finely divided than in Henodus, and the overall structure was not quite as complete. Siamodus also retained more substantial teeth than Henodus, still in the placodont tradition of crushing hard prey, though the teeth were somewhat reduced compared to Placodus. Siamodus represents a middle stage, an animal that was clearly moving in the direction of Henodus, but had not yet arrived there. Then there were animals like Cephiderma, which lived at roughly similar times to Henodus, and also developed a highly elaborate shell. Cephiderma had a two-part shell, a division between a front section covering the shoulders and a rear section covering the hips and back, with a gap between them that allowed some flexibility. The shell was formed from fine polygonal osteoderms, similar in texture to Henodus, and the overall silhouette was again strikingly turtle-like. Cephiderma shows that the extreme armoured form was not unique to Henodus within the Chiamodontoids. Multiple lineages were converging on the same general body plan at roughly the same time, responding to the same broad pressures. What were those pressures? Predation is the most obvious answer, and it is probably the right one, at least in part. The Triassic seas were not empty. Nothosaurs were long-necked, agile marine reptiles that were common in the Tethys during this period, and they were capable predators with sharp teeth and fast movement. Ichthyosaurs, the dolphin-shaped marine reptiles, were also present and diversifying rapidly through the Triassic. Large predatory fish were part of the ecosystem. Any slow-moving, bottom-feeding reptile living in shallow coastal waters would have been a plausible target for all of these. The armour in this context is not a puzzle, it is a response. An animal that cannot outswim its predators needs another way to survive, and a shell that cannot be bitten through is a very effective alternative to speed. But predation pressure alone may not be the complete picture. The environments where the most heavily armoured placodonts lived, including the hypersaline lagoons where Henodus is found, were not places where large predators were common. The Gipscooper lagoon was, as we have already seen, a stressed environment where the salinity and low oxygen levels would have excluded many larger animals. So the armour that Henodus carried into that lagoon may have been inherited from ancestors who lived in more exposed predator-rich environments and then retained even after Henodus moved into a habitat where it was less immediately necessary. This is not unusual in evolution. Traits that evolve under one set of pressures can persist long after those pressures have changed, especially if they are not costly enough to be selected against. The armour was heavy, but it was also functional, and in an environment where the occasional predator might still wander in from the open Tethys, keeping it was probably still worthwhile. Henodus itself, appearing around 230 to 228 million years ago, represents the end point of this trend. By the time Henodus evolved, the Chiamodontoid lineage had been developing armour for roughly 15 million years. The incremental changes across that span, more osteoderms, finer divisions, more complete coverage, better integration of the carapace and plastron, had accumulated into an animal whose shell was as complete and as structurally sophisticated as anything the Placodont lineage ever produced. The polygonal mosaic of small bony plates covering Henodus was not just protective. It was elegant in its own way, a finely tessellated surface that distributed stress evenly across the shell and resisted deformation under pressure. The engineering of it, arrived at without any engineer, through nothing but the slow accumulation of small inherited changes, is genuinely impressive. What is also worth noting is that Henodus was not simply the most armoured placodont. It was also the one that had moved furthest from the original placodont dietary strategy. While Placidus was a dedicated hard prey crusher with impressive crushing teeth, and while intermediate forms like Siamodus still retained significant dentition, Henodus had almost abandoned teeth entirely. The single, small tooth on each side of the jaw was a vestige, not a functional crushing tool. The keratinous beak had taken over almost completely. This dietary shift and the armour evolution happened together, which suggests they were part of the same broader ecological transition. Henodus was not just the most armoured placodont, it was also the most ecologically divergent, the one that had moved furthest from the ancestral lifestyle and into a new niche that we still do not fully understand. The duration of the fully armoured placodonts was relatively short on geological timescales. From the earliest chiamodontoids to the end Triassic extinction that wiped them all out, the armoured placodonts existed for roughly 40 to 45 million years. Henodus itself, at around 230 to 228 million years ago, had only about 27 to 29 million years before the extinction that ended the whole experiment. That is not a trivial span of time, and it is long enough that Henodus and its relatives were genuinely successful animals, not marginal failures clinging to existence at the edge of viability. They thrived in their specific environments, diversified into multiple lineages, and produced some of the most structurally remarkable animals of the Triassic marine world. The fact that they are gone now does not diminish that success. It simply reminds us that success in evolutionary terms is always conditional and always temporary. There is something worth sitting with in the trajectory of the chiamodontoid lineage. It is a story of progressive specialization, each generation slightly more armoured, slightly more committed to the bottom-dwelling, slow-moving, heavily protected lifestyle. Until the endpoint was an animal so thoroughly adapted to that strategy that it had essentially become a different kind of creature from the unarmoured ancestors it descended from. Placidus and Henodus were both placodonts, both members of the same broader lineage, but they were ecologically so different that if you encountered them without any background knowledge, you would not immediately recognise them as closely related. One was a robust, lizard-like, tooth-heavy animal moving through open coastal waters. The other was a flat, armoured, nearly toothless animal resting on the bottom of a hypersaline lagoon. The distance between them, covered in roughly 15 million years of gradual change, is a reminder of how far evolution can move a lineage when the pressures are consistent and the direction is clear. The armour evolution within chiamodontoids also raises a question that paleontologists have spent some time thinking about. If multiple lineages within the group independently evolved elaborate shells, does that mean the underlying genetic and developmental machinery for armour production was already present in the common ancestor, waiting to be activated? This is a concept sometimes called developmental constraint, or, more positively, developmental potential. The idea is that some evolutionary pathways are easier to take than others, because the molecular and developmental tools needed to go in that direction are already available. Osteoderms, the bony skin plates that form placodont armour, are not unique to placodonts. They appear in many reptile lineages, including crocodilians, some lizards, and various archosaurs. The developmental pathway for producing osteoderms was already part of the reptile toolkit. What the chiamodontoids did was take that existing toolkit and push it further, producing more osteoderms, arranging them more systematically, integrating them into a more complete structure. The direction was new, but the tools were old. This may be part of why the armouring trend happened multiple times within the group. Once the basic machinery was in place, the path toward more elaborate armour was relatively accessible, and different lineages took it independently because the selective pressure to do so was present across the whole group. This connects back once again to the broader theme of convergent evolution that runs through the entire Henodus story. Convergence is not just something that happens between distantly related animals like placodonts and turtles. It also happens within lineages, between closely related groups that share developmental tools and face similar pressures. The chiamodontoids show convergence at multiple scales simultaneously, Within the group, as different lineages independently evolved elaborate armour, and between the group and turtles, as the placodont lineage as a whole arrived at a body plan that resembles the turtle body plan, despite having nothing to do with it developmentally. It is a nested pattern of repeated solutions, and Henodus sits at the centre of it, the most extreme expression of the inner convergence and the most striking example of the outer one. The end of the Siamodontoids, when it came around 201 million years ago, was not a gradual fading. It was a sudden cut, the end Triassic extinction erasing the entire group along with much else. But that is a story for the next part of this journey, because the extinction itself is worth understanding on its own terms, not just as the moment when Henodus disappeared, but as one of the most dramatic events in the history of life on Earth, and one whose causes and consequences are still being carefully worked out by geologists and paleontologists today. The end Triassic extinction is one of those events in Earth history that does not always get the attention it deserves. Most people, if they think about mass extinctions at all, tend to think of the one that ended the dinosaurs 66 million years ago, the asteroid impact, the dust cloud, the sudden darkness. That one has a certain dramatic clarity to it. A rock fell from space. Things died. The story is terrible but comprehensible. The end Triassic extinction, which happened around 201 million years ago, is less clean in its narrative, less photogenic in a way, but it was genuinely catastrophic. It is counted among the 5 largest mass extinctions in the history of complex life on Earth, and it reshaped the planet's ecosystems in ways that echoed for millions of years afterward. It was not an asteroid. It was something slower, and in some ways more unsettling. The primary driver, as far as current evidence indicates, was a period of massive volcanic activity associated with what geologists call the Central Atlantic Magmatic Province, or CAMP. This was one of the largest volcanic events in geological history, a prolonged episode of eruptions that accompanied the beginning of the breakup of the supercontinent Pangaea. As Pangaea began to split apart, enormous quantities of magma flooded to the surface across a region that would eventually become parts of North America, South America, Europe, and Africa. The lava flows themselves were vast, covering areas measured in millions of square kilometres. But the lava was not the most dangerous part. What came out of the eruptions along with the lava was the real problem. Carbon dioxide, sulfur dioxide, and other gases, in quantities large enough to alter the chemistry of the entire atmosphere and ocean. Carbon dioxide in large quantities causes warming. It also causes ocean acidification, because carbon dioxide dissolves in seawater and forms carbonic acid, which lowers the pH of the ocean. For marine organisms that build shells or skeletons out of calcium carbonate, acidification is a serious problem. It makes it harder to build and maintain those structures, and in severe cases, it begins to dissolve them. The end Triassic Ocean was not a friendly place for anything that relied on calcium carbonate. Coral reefs largely collapsed. Many groups of marine invertebrates were hit hard. The disruption cascaded through food webs in ways that are still being traced by researchers studying the geological record of this period. Sea level changes added to the problem. The same volcanic activity that was flooding the atmosphere with carbon dioxide was also driving changes in ocean circulation and sea level. Shallow coastal environments, which had been rich and productive through much of the Triassic, were disrupted. Lagoons dried up or changed dramatically in chemistry. The marginal marine environments that had supported so much Triassic biodiversity became unstable. For placodonts, all of this was essentially a perfect storm of bad conditions. They were already highly specialised animals. Henodus, in particular, was adapted to a very specific kind of environment: shallow, hypersaline lagoons on the margins of the Tethys Sea. These were not robust, flexible ecosystems. They were already stressed environments, already operating near the edge of what could support complex animal life. When the broader disruption of the end Triassic extinction hit, those lagoon systems would have been among the first to collapse or transform beyond recognition. The food sources Henodus depended on, whatever they were, algae, soft invertebrates, filter-feeding substrates would have been disrupted. The water chemistry that Henodus was adapted to would have shifted. There would have been nowhere to go, no adjacent habitat to retreat into, no deeper ocean refuge available to an animal built for shallow bottoms. Slow reproduction likely made things worse. We do not have direct evidence of how placodonts reproduced, but heavily built armoured reptiles tend toward relatively slow life histories. Large body size, heavy armour, and bottom-dwelling lifestyles are generally associated with fewer offspring, longer development times, and lower population turnover. This matters enormously during an extinction event. Species that can reproduce quickly, that can produce large numbers of offspring in a short time, have a better chance of recovering from population crashes. If a population drops by 90% but can rebuild within a few generations, it may survive. If a population drops by 90% and takes decades to recover, it almost certainly will not. Placodonts, if they were anything like their ecological equivalents today, were probably in the slow category. Mobility is another factor worth thinking about. Plesiosaurs and ichthyosaurs, which did survive the end Triassic extinction and went on to diversify through the Jurassic, were open ocean animals. They were fast, wide-ranging, and capable of moving across large distances in search of food and suitable conditions. When conditions deteriorated in one area, they could move. When prey population shifted, they could follow. They were not locked into a single habitat type. Henodus was, by contrast, a slow-moving, heavily armoured, bottom-dwelling animal adapted to a very specific kind of shallow enclosed environment. It could not simply swim out into the open ocean and find a new lagoon somewhere else. The architecture of its body was built for one kind of life, in one kind of place, and when that kind of place became untenable, there was no alternative available. There is something quietly sobering about this. Specialization is, in many ways, the story of evolutionary success. Henodus was extraordinarily well adapted to its environment. Its armour protected it from the predators that might have threatened it. Its beak, whatever it was doing with it, was presumably well suited to the food available in its lagoon. Its heavy bones kept it anchored to the bottom where it fed. Its flat, wide body reduced drag in shallow water. Every feature of its anatomy was a solution to a specific problem posed by a specific environment. And then the environment changed, not gradually, not in a way that left room for adaptation, but suddenly, on geological timescales that left no time for the slow machinery of natural selection to find a new direction. The very specialization that had made Henodus successful became the thing that made it unable to survive. This is a pattern that appears repeatedly in the fossil record, and it is worth pausing on it for a moment. The most highly specialized animals are often the most impressive, the most structurally elaborate, the most finely tuned to their circumstances. They are also, in many cases, the most fragile when circumstances change. The generalists, the flexible, the mobile, the animals that can eat a variety of things and live in a variety of places, tend to weather disruptions better. Not because they are better animals in any absolute sense, but because their very lack of specialization is itself a kind of resilience. Henodus was not a failure. It was, in its time and place, a remarkable success. But success built on narrow foundations does not survive when those foundations are removed. The geological evidence for the end Triassic extinction is visible in rock formations around the world, and the Triassic-Jurassic boundary is one of the more clearly defined boundaries in the geological record. In many sections, there is a dramatic shift in fossil assemblages across a relatively thin layer of rock. Below the boundary, Triassic fauna. Above it, a very different collection of animals. Placodonts appear below the boundary. They do not appear above it. Not anywhere. Not in any formation, not in any part of the world. The last placodont fossils are Triassic, and then the group simply stops. There is no Jurassic placodont, no lingering population that held on in some sheltered corner of the ocean. The extinction was total for this group. This completeness is itself informative. some groups that were severely reduced by the end Triassic extinction managed to persist in small numbers and eventually recover. Others were simply gone. The fact that placodonts left no survivors at all suggests that whatever combination of factors hit them, it hit them everywhere simultaneously. There was no refugium, no isolated population that escaped the worst effects. The lagoons and shallow coastal environments they depended on were disrupted broadly enough that no population made it through. It is worth noting that the end Triassic extinction, while devastating, was also in a strange sense a clearing event. The Jurassic period that followed was, in many ways, a world of opened doors. With so many niches vacated by extinction, the survivors had room to expand, diversify, and explore ecological territory that had previously been occupied. Plesiosaurs, which had been present in the Triassic but were not the dominant marine reptiles of that period, expanded dramatically in the Jurassic and became the iconic long-necked predators of Jurassic seas. Ichthyosaurs, already successful in the Triassic, continued to diversify. Dinosaurs, which had been relatively minor players in the Triassic terrestrial ecosystem, became the dominant large land animals of the Jurassic. The world that emerged from the end Triassic extinction was in many ways more familiar to us, because it was the world that eventually led to the Mesozoic ecosystems that most people picture when they think of prehistoric life. But in that new world, there were no placodonts. The ecological niche that Henodus and its relatives had occupied, the heavily armoured, slow-moving, shallow water bottom dwellers of the Tethys margins, went unfilled for a long time. Turtles, which would eventually become the dominant armoured, slow-moving, shallow-water reptiles of the world's coastlines, were present in the Triassic but had not yet diversified into the range of marine and semi-aquatic forms they would later produce. The marine turtle radiation, the expansion of turtles into open ocean and coastal marine environments, happened largely in the Cretaceous, tens of millions of years after the placodonts were gone. In the interval, the niche was simply vacant. No other group stepped in to fill it immediately. The Jurassic seas had plenty of large marine reptiles, but none of them were doing what Henodus had been doing. That particular ecological experiment had ended, and it would not be repeated in quite the same way. There is one more thing worth considering about the placodont extinction, which is the question of what we actually know versus what we are inferring. The fossil record for placodonts is not dense. We have a reasonable number of specimens from a handful of species, but there are certainly gaps. It is possible that some placodont lineages persisted slightly longer than the current fossil record indicates, in areas or depositional environments that have not been well sampled. The absence of Jurassic placodont fossils is strong evidence, but absence of evidence is not always evidence of absence, especially for groups that lived in restricted coastal environments where fossilization was never guaranteed. Most paleontologists working on this group do accept that placodonts were extinct by the end of the Triassic, and the evidence supports that conclusion. But it is worth holding the conclusion with appropriate care, as a well-supported inference rather than an absolute certainty. What is certain is that from the moment the end Triassic extinction closed the book on the placodonts, no animal quite like Henodus has ever appeared again. The specific combination of features, the nearly toothless beak, the mosaic osteoderm shell, the flat, wide body, the hypersaline lagoon habitat, the bottom-dwelling lifestyle, was a unique product of a unique moment in Earth's history. The Triassic was a peculiar time, a world still recovering from the even larger Permian extinction, still assembling its ecosystems, still working out which body plans would succeed and which would eventually be abandoned. It was a time of experiments, and Henodus was one of the more striking ones. The fact that the experiment ended does not make it less remarkable. If anything, knowing that this animal existed for only a relatively brief window, that it appeared, thrived, and vanished within the Triassic, makes the fossil record of it feel more precious. The single specimen sitting in its repository in Tübingen is not just a scientific object. It is the only physical trace of an entire way of being alive that the world tried once and never tried again. And yet, Even though the animal itself is gone, the questions it raises have not gone away. Scientists working today are still finding new things to learn from Henodus, not just about the animal itself, but about the broader questions of how evolution works, how body plans arise, and how the fossil record can be read with modern tools that Friedrich von Huene could never have imagined in 1936. That part of the story, the modern scientific work on this creature, is where things get quietly interesting in a different way. The specimen itself has never moved far from where it was first studied. The holotype of Henodus Keliops, that single, nearly complete skeleton recovered from the Gipskuper limestone near Tübingen in 1936, remains in Germany, housed and preserved as it has been for the better part of a century. Friedrich von Huene described it as best he could with the tools available to him at the time, and his original description was thorough, careful, and genuinely impressive for its era. But the tools available to a paleontologist in 1936 were, by modern standards, quite limited. You could look at a fossil, you could measure it, you could compare its visible surfaces to other specimens, you could draw it, describe it, and place it within the classification schemes of the day. What you could not do was look inside it without destroying what you were looking at. That limitation shaped everything about early interpretations of Henodus, and it is one of the reasons why the animal continued to generate questions long after von Huene's initial description was published. The shift began gradually, as it often does in paleontology, not with a single dramatic discovery, but with the slow accumulation of better methods applied to existing material. Computed tomography, the same basic technology used in medical imaging, became available to paleontologists in a meaningful way during the 1990s and expanded significantly in the 2000s. A CT scanner can pass X-rays through a dense object from multiple angles and reconstruct a three-dimensional image of its internal structure without touching the object at all. For a fossil locked in matrix, or for a specimen where the internal bone architecture matters for understanding function, this is transformative. You can look inside the skull of an animal that died 230 million years ago and see the shapes of the brain cavity, the inner ear structures, the pathways of blood vessels and nerves, all without cutting a single slice through the rock. Applied to Henodus, CT scanning has allowed researchers to examine the internal structure of the skull in ways that von Huene simply could not. The skull of Henodus is small and somewhat compressed, which made surface examination of certain features difficult. Internal structures that could only be guessed at from the outside can now be mapped with reasonable precision. The bony architecture around the jaw joint, the arrangement of bones forming the palate, the overall geometry of the brain case. These details matter for understanding how the animal fed, how it processed sensory information, and how it relates to other placodonts and to the broader Sauropterygia. Some of these internal features have helped clarify the phylogenetic position of Henodus, which sounds like a dry technical point but is actually quite important. Knowing exactly where an animal sits in the family tree of life determines what its features can tell us about evolution, about the direction of change over time, and about what it shares with its relatives versus what it evolved independently. The shell has also received renewed attention. The osteoderm mosaic that forms the carapace of Henodus is not a simple structure. Each individual osteoderm is itself a small bony element with its own internal architecture, its own growth pattern, its own relationship to the elements around it. Studies of the microstructure of these bones, looking at how they were laid down during the animal's growth, how they fused or articulated with neighbouring elements, and how the overall mosaic achieved the rigidity it needed to function as armour, have added considerable detail to the picture. One of the things microstructure studies can reveal is something about growth rates. Bone tissue laid down quickly tends to look different from bone tissue laid down slowly, and these differences are preserved in the fossil. While drawing firm conclusions from a single specimen is difficult, the bone microstructure of placodonts generally, including what can be assessed in Henodus, suggests growth patterns that were neither extremely fast nor extremely slow by reptile standards. This is a modest finding, but it is the kind of modest finding that accumulates into a broader understanding over time. The name most consistently associated with modern placodont systematics is Olivier Riepel, a Swiss paleontologist who spent much of his career at the Field Museum in Chicago and who produced a substantial body of work on Triassic marine reptiles, including detailed analyses of placodont phylogeny. Riepel's work on placodonts spans several decades and includes both descriptive studies of individual specimens and broader phylogenetic analyses that attempt to map the evolutionary relationships within the group and between placodonts and other sauropterygians. His analyses have been refined and sometimes revised by subsequent researchers, as is normal in science, but they established a framework that later work has built upon. The placement of Henodus within the siamodontoid placodonts, the armoured branch of the group, is well established in part because of this systematic work, and the relationship of chiamodontoids to earlier, unarmoured placodonts like Placodus has been worked out in enough detail that we can trace, at least in broad outline, the evolutionary sequence that produced an animal like Henodus. What these phylogenetic analyses have also clarified is something that might seem counterintuitive at first. The extreme armour of Henodus, its shell-like carapace and plastron, did not evolve all at once. It was the endpoint of a gradual process that can be traced through the chiamodontoid lineage. Earlier chiamodontoids had armour, but it was less extensive, less integrated, and less turtle-like. As the lineage progressed through the Triassic, the armour became more complete, the individual osteoderms became more tightly interlocked, and the overall body plan became more flattened and more enclosed. Henodus sits at the far end of this trajectory, representing the most fully developed version of the chiamodontoid body plan. This makes it both the most extreme member of its group and the most visually striking, which is part of why it has attracted so much attention from researchers and from anyone who encounters a reconstruction of it for the first time. There is also ongoing work on the jaw mechanics and feeding biology of Henodus, a question that has never been fully resolved. The toothless beak, or nearly toothless beak, is such an unusual feature for a placodont that it demands explanation. Most analyses of jaw function in fossil animals rely on a combination of bone geometry, muscle attachment scars, and comparison with living animals that have similar structures. For Henodus, the comparison animals are limited, because there is nothing alive today that combines a heavily armoured reptile body with a wide flat beak and a bottom-dwelling aquatic lifestyle in quite the same configuration. Modern sea turtles have beaks and live in water, but their overall biology is different enough that direct comparison has limits. Modern rays have flat bodies and feed on the bottom, but they are fish, not reptiles, and their jaw structures are completely different. Researchers working on Henodus feeding have had to be creative in their comparisons, drawing on multiple living animals and multiple lines of evidence to construct a picture that is plausible, but remains genuinely uncertain. The filter feeding hypothesis, the idea that Henodus may have used its wide beak to strain food from water or sediment, has attracted interest, but also skepticism. True filter feeding in aquatic animals typically involves either very fine structures for straining small particles, like the baleen of whales, or a large gape and rapid water intake like the feeding of whale sharks. The jaw anatomy of Henodus does not obviously support either of these mechanisms. The alternative hypotheses, suction feeding on soft-bodied invertebrates, or even some form of plant or algae consumption, each have their own anatomical arguments for and against. What seems clear is that Henodus was doing something very different from the shellfish crushing that characterised most of its placodont relatives, and that whatever it was eating, the jaw was adapted for a scooping, pressing or filtering motion, rather than for hard object crushing. The exact nature of that food source may remain unknown without additional specimens or new analytical techniques that have not yet been applied. This brings up the most fundamental limitation of Henodus research, which is the single specimen problem. Almost everything we know about this animal comes from one individual. One set of bones, one skull, one shell, one set of limbs. This is not unusual for Triassic marine reptiles, many of which are known from fragmentary or single specimens. But it does place real constraints on what can be concluded. When you have only one individual, you cannot assess variation within the species. You cannot tell whether the features you're looking at are typical of all Henodus individuals, or whether this particular animal was unusual in some way. You cannot determine the range of adult body sizes, because you do not know whether your specimen was fully grown. You cannot say anything about sexual dimorphism, because you have no way to determine the sex of the animal or compare individuals. You cannot assess geographic variation, because you have no specimens from other locations to compare. Some of these limitations are simply unavoidable given the fossil record. The Gipskuiper Formation near Tübingen has been examined and collected for many decades, and no additional Henodus specimens have come to light. Either the animal was genuinely rare in this environment, or the conditions for preservation were such that most individuals were not fossilized, or the right deposits have not yet been found and excavated. All three of these explanations are plausible, and they are not mutually exclusive. It's entirely possible that Henodus was a relatively uncommon animal, even in its own time, living in a restricted and stressed habitat that did not support large populations. Hypersaline lagoons, by their nature, are not highly productive environments. They support specialized communities of organisms, but not usually in large numbers or with high diversity. An animal living in such an environment might simply have been rare, and rare animals leave fewer fossils. The possibility that additional specimens exist somewhere, either in unexcavated deposits or in collections that have not been fully studied, is always present. Paleontology has a long history of significant specimens sitting in museum drawers for decades before someone recognizes what they are. The Gipskuiper and related Triassic formations extend across parts of Central Europe, and not all of them have been systematically searched for placodont material. It is not unreasonable to hope that future fieldwork or collection review might turn up additional Henodus material, or at least material from closely related animals that could fill in some of the gaps. But as of now, the holotype specimen described by von Huene in 1936 remains the only confirmed Henodus individual, and it carries the full weight of everything we know about the species. Modern imaging techniques have done what they can with this single specimen. Beyond CT scanning, photogrammetry, the process of creating precise three-dimensional digital models from photographs taken from multiple angles, has been applied to various placodont specimens, including material related to Henodus. These digital models allow researchers to share data across institutions, to make precise measurements that would be difficult on the physical specimen, and to conduct virtual analyses of bone geometry and mechanical properties. The digitization of fossil collections more broadly has made it easier for researchers who are not physically located in Tübingen to work with Henodus material, which has expanded the number of people who can contribute to understanding the animal. What remains stubbornly out of reach, and this is true of almost every fossil animal, is the soft biology. We do not know what colour Henodus was. We do not know how it reproduced, whether it laid eggs on land like many reptiles, or whether it gave birth to live young in the water as some other marine reptiles did. We do not know how it behaved socially, whether it was solitary, or whether individuals aggregated in certain areas. We do not know how long it lived, what its metabolic rate was, how it responded to the seasonal changes in its lagoon environment, or how it died. The fossil record gives us bones, and bones are remarkable things, but they are also only one part of an animal. The rest, the muscles, the skin, the organs, the behaviours, the sounds if it made any, the interactions with its environment day to day, all of that is gone. We reconstruct what we can from what remains, and we acknowledge the rest as unknown. There is something quietly sobering about this, but also something that keeps the science moving. Every new technique, every new analytical approach, every new specimen from a related animal adds a small piece to the picture. The picture of Henodus today is considerably more detailed and more reliable than the one von Wien could draw in 1936. And the picture that researchers will have in another 50 years will almost certainly be more detailed still. Science on fossil animals is not a project with a fixed endpoint. It is an ongoing process of refinement, correction, and expansion, driven by new tools, new questions, and occasionally new discoveries. What is striking about the modern study of Henodus is not just the technical sophistication of the methods being applied, but the range of questions those methods are being used to answer. This is no longer simply a matter of describing bones and assigning a name. Researchers are asking about growth, about function, about behaviour, about ecology, about evolutionary mechanism. They are using Henodus as a data point in much larger arguments about how body plans evolve, how convergence works at a mechanistic level, and what the Triassic marine world actually looked like in detail. The animal that von Huene pulled from the limestone near Tübingen has turned out to be a remarkably productive scientific object, generating questions and insights well beyond what its discoverer could have anticipated. And those questions, the bigger ones about what Henodus means as an example of how life works, reach well beyond the boundaries of Triassic paleontology. They touch on some of the most interesting and actively debated topics in evolutionary biology. Questions that have implications not just for understanding the past, but for thinking about the nature of life itself. That broader conversation is where the story of Henodus opens up into something larger than the single, flat-bodied, beak-jawed, armoured creature resting on the bottom of a Triassic lagoon. It is a conversation about patterns, about inevitability, about what evolution can and cannot do when faced with the same problems again and again across millions of years. And that is the conversation worth following next. So let us follow that conversation for a moment, because it leads somewhere genuinely interesting. Convergent evolution is one of those concepts that sounds straightforward when you first encounter it, but becomes more and more remarkable the longer you sit with it. The basic definition is simple enough: unrelated lineages, facing similar environmental pressures, independently arrive at similar solutions. Same problem, same answer, different route. But what makes it striking is not the definition. It is the frequency. It is how often this happens, how reliably it happens, and what that reliability seems to be telling us about the nature of life itself. Henodus is one of the clearest examples in the fossil record. Here is an animal that shared no recent common ancestor with turtles, that evolved its shell through a completely different developmental pathway, that lived in a different ocean at a different time with a different diet, and yet arrived at a body plan so similar to a turtle's that the first scientists who described it spent considerable effort explaining why it was not one. The carapace, the flat wide body, the paddle limbs, the short tail, the beaked jaw, these features appeared independently, built from different biological raw materials, shaped by different evolutionary pressures working over different timescales. And yet the end result was, to any casual observer, a turtle. The developmental difference is worth dwelling on, because it is one of the things that makes this convergence so technically impressive. A turtle's shell is not armour in the conventional sense. It is the turtle's own rib cage, dramatically modified. During turtle embryonic development, the ribs broaden and fuse together, and the vertebrae participate in this fusion as well, creating a bony structure that is literally part of the animal's skeleton in the most intimate way possible. The shell is not something a turtle wears. It is something a turtle is. The developmental pathway that produces this structure is ancient and deeply embedded in turtle biology, and it took a long time to evolve. Henodus's shell came from somewhere else entirely. It came from osteoderms, small bony elements that formed within the skin, independent of the underlying skeleton. Osteoderms are common in many reptile groups. Crocodilians have them. Many lizards have them. Some dinosaurs had them. They are a general-purpose reptilian toolkit for adding armour. What the Placidont lineage did was elaborate this toolkit to an extraordinary degree, packing the osteoderms together into a dense, interlocking mosaic that covered the back and belly of the animal and produced, from the outside, something that looked remarkably like a turtle shell. Different genes, different developmental processes, different evolutionary history, same shape. This is what biologists mean when they talk about convergence as evidence of something deeper than coincidence. If two completely different lineages working with different tools arrive at the same solution, it suggests that the solution is in some sense optimal, or at least very good, for the problem being solved. The flat-armoured body is not an accident. It is an answer. And the question it answers, how do you survive as a slow-moving animal in shallow water with predators around, turns out to have a fairly limited number of good responses. You can be fast, which requires a very different body plan. You can be cryptic, which helps but is not always sufficient. Or you can be heavily armoured and low profile, making yourself too difficult and too unrewarding to attack. Turtles found this answer. Placodonts found this answer. And they found it independently, across tens of millions of years of separation, because the answer was there waiting to be found. This kind of reasoning has started to interest people well beyond paleontology. Astrobiologists, researchers who think about the conditions under which life might exist elsewhere in the universe, have taken convergent evolution seriously as a line of argument. The logic runs roughly like this. If evolution on Earth repeatedly produces the same solutions to the same problems, then perhaps certain body plans, certain functional designs are not just possible but in some sense inevitable, given the right conditions. If you have a shallow, warm, predator-filled aquatic environment, you might expect armoured, slow-moving animals to appear, regardless of what evolutionary lineage is doing the evolving. If you have an open, aerial environment with food to be caught, you might expect wings to appear, regardless of whether the lineage in question is a bird, a bat, or a pterosaur. The solution is written into the physics and ecology of the situation, and evolution reads that writing and responds. Wings are perhaps the most often cited example of convergence, and for good reason. Powered flight evolved independently at least 4 times in vertebrates alone, in pterosaurs during the Triassic, in birds from theropod dinosaurs during the Jurassic and Cretaceous, in bats during the early Paleogene, and arguably in various gliding forms that represent intermediate stages. Each of these lineages modified forelimbs into wings using different anatomical starting points. Pterosaur wings were supported by an enormously elongated 4th finger. Bird wings are built around fused hand bones and supported by feathers, which are themselves a modified form of reptilian scale. Bat wings stretch a membrane of skin across multiple elongated fingers. 3 different architectural solutions, all producing the same functional outcome, sustained powered flight. The sky, like the shallow lagoon, seems to have a preferred answer to the question of how to move through it efficiently. The eye is another case that biologists return to again and again, partly because it is so counterintuitive. The vertebrate eye, the kind of eye you're using right now if you're reading rather than listening, is a complex structure with a lens, a retina, photoreceptor cells, and a sophisticated neural connection to the brain. It took a long evolutionary history to produce. The cephalopod eye, found in octopuses and squid, looks almost identical from the outside and performs very similar functions, but evolved completely independently. The 2 lineages that produced these eyes diverged from a common ancestor that almost certainly had nothing more than a simple light-sensitive patch of cells. Everything above that primitive beginning was built separately, in parallel, over hundreds of millions of years, and yet the camera-style eye appeared twice, because the camera-style eye is simply a very good way to see in a world where light behaves the way light behaves. Henodus sits in this company quietly. It is not as dramatic as the eye, perhaps, and not as immediately striking as the wing. But it belongs to the same category of evidence. It is one more data point in the accumulating argument that evolution, for all its contingency and randomness at the genetic level, produces recognizable patterns at the level of whole organisms. The randomness is real. Mutations are genuinely unpredictable, and the history of any lineage is shaped by accidents of geography, climate, and chance encounters with predators and prey. But the randomness operates within constraints, and those constraints are physical, ecological, and chemical. They are the constraints of what bodies can do, what environments reward, and what physics permits. And within those constraints, certain solutions keep appearing. There is something almost philosophical about this, and it is worth sitting with it for a moment rather than rushing past. The idea that evolution has a kind of deep logic, that it is not simply a random walk through biological possibility space, but a process that is drawn toward certain stable solutions, changes how you think about the history of life. It suggests that the particular animals we know, the turtles, the placodonts, the bats, the pterosaurs, are not the only possible inhabitants of their ecological roles. They are instances of solutions that could have been found by other lineages, and in many cases were. The turtle-shaped animal is not a turtle-specific invention. It is a shape that the world seems to call forth under the right conditions. Henodus is evidence of that. This also has a slightly humbling implication for the way we think about our own moment in the history of life. We tend to look at the animals alive today and treat them as the natural and inevitable products of evolution, as if the particular forms we know are the only ones that could have filled their roles. But the fossil record shows us that many of those roles have been filled before by very different animals, using very different designs. The turtle-shaped niche was occupied by placodonts, before turtles became common in marine environments. The dolphin-shaped niche was occupied by ichthyosaurs before dolphins existed. The large flightless bird niche has been filled multiple times by unrelated lineages on different continents. The world has a limited number of good ecological roles, and evolution fills them repeatedly, with whatever raw material happens to be available. What Henodus adds to this picture is a particularly clean example, because the convergence is so complete and so well documented. We have the fossil, we have the comparative anatomy, we have the developmental biology of turtles for comparison. We have the phylogenetic analysis that firmly places Henodus outside the turtle lineage, and we have the ecological context, the shallow, warm, hypersaline lagoon, that explains why a flat-armoured body was a good idea in that place and time. All the pieces are present. The case is about as well supported as a convergence argument can be, given the limitations of the fossil record. There is also something worth noting about what Henodus does not tell us, because this is part of how science works honestly. Convergent evolution shows us that certain solutions are repeatedly discovered, but it does not tell us that those solutions are inevitable in a strict sense. There were probably many Triassic lagoons that never produced a Henodus-like animal. There are modern shallow marine environments that do not contain turtle-shaped reptiles. The conditions that favour a particular solution need to be present, and they need to persist long enough for selection to act, and the lineage in question needs to have the genetic and developmental raw material to respond in the right direction. Convergence is common, but it is not guaranteed. The fact that placodonts and turtles both arrived at a similar shape is remarkable precisely because it did not have to happen. It happened because the conditions were right and the biology was capable. That combination is not always present, and when it is, the result is something worth paying attention to. Henodus, then, is a quiet but compelling argument, not a loud one. It does not demand attention. It rested on the bottom of its lagoon for 230 million years before anyone found it, and it has been sitting in the scientific literature, sometimes overlooked, since 1936. But the argument it makes is a strong one. It says that the history of life is not simply a record of what happened to exist. It is also a record of what works. And what works tends to appear again, in different forms, in different times, wearing different names and built from different materials, but recognisable nonetheless. The flat-armoured body, the wide jaw, the paddle limbs, the slow life on the bottom of a warm, shallow sea. These are not turtle inventions. They are solutions. And solutions, it turns out, have a way of being rediscovered. It is a thought that makes the single specimen in Tübingen feel like more than a curiosity. It makes it feel like a demonstration. One slow, armoured, beak-jawed animal, preserved by luck in a limestone bed in southern Germany, carrying in its bones a lesson about the deep structure of evolutionary possibility. That lesson is still being read, still being refined, still generating new questions in laboratories and field sites and conference rooms. And the next question it raises is perhaps the most personal one the story has to offer. The question of how close we came to never knowing any of this at all. And that question, the question of how close we came to never knowing any of this at all, is not a rhetorical one. It is genuinely worth sitting with, because the answer is uncomfortably close. We know Henodus from a single specimen, one animal, one set of bones, preserved in one specific layer of fine-grained limestone in one quarry near Tübingen in southern Germany, found by one scientist in one particular year. Friedrich von Huene was there in 1936 because he was already working in the region, already familiar with the Triassic deposits of the Gipskuper Formation, already one of the most experienced vertebrate paleontologists in the world. He recognised what he was looking at. He knew it was unusual, he published carefully, and because of all of that, we have Henodus. But think about how many things had to go right for that to happen. The animal had to die in a place where preservation was possible. Not all environments preserve bones. Most don't. The soft, fine-grained limestone of the Tübingen deposit is exactly the kind of sediment that captures detail. The same reason it preserved the mosaic of the shell, the shape of the skull, the outline of the limbs. If Henodus had died in coarser sediment, or in open water where the bones scattered before burial, or in an environment where the chemistry was wrong, there would be nothing to find. The bones would have dissolved, or been scattered, or simply never mineralized at all. Then the deposit had to survive. 230 million years is a long time. The rocks that contain Henodus have been compressed, tilted, and moved by tectonic forces. They have been eroded at the surface and buried deeper at other points. They happen to be exposed in a form accessible to excavation in the 20th century. A slightly different geological history, more erosion, a different angle of uplift, a deeper burial, and the fossil might never have reached the surface in a recognisable form. Then the quarry had to be worked in a way that exposed the fossil without destroying it. Limestone has been quarried in that region for centuries, for building materials, for lime production, for road construction. Heavy machinery does not distinguish between ordinary rock and a 230-million-year-old skeleton. The specimen survived intact, which is remarkable. It came out nearly complete, which is rarer still. The conditions of its discovery were, in a quiet way, almost improbably fortunate. And then von Huene had to be there. Someone had to be present who could recognise the significance of what the rock contained, who had the training and the instinct to stop and look carefully rather than pass over it as an interesting but unimportant fragment. Paleontology depends on this kind of human attention in a way that other sciences sometimes don't. The fossil does not announce itself. It sits in the rock and waits, and it is only found if the right person happens to be looking at the right place at the right time. Von Huene had spent decades developing exactly that kind of attention. He had named and described dozens of Triassic reptiles. He understood the formations. He understood what was typical and what was not. When he saw the wide flat carapace, the small skull, the paddle-like limbs, he understood that this was something that needed careful documentation, and he gave it that documentation. His 1936 description of Henodus sceliops remains the foundational reference for everything that has come after. This is not a small thing. Scientific knowledge about extinct animals exists only because specific people, in specific places, at specific times, chose to look carefully and record what they found. The fossil record is not a database that fills itself. It is built one discovery at a time, by people working in difficult conditions, often in remote places, often with limited funding, often without knowing in advance whether what they're searching for will turn out to be significant. Von Huene could not have known, when he began excavating that deposit, that it contained the most extreme example of turtle-like convergence in the entire Triassic. He found out by looking. What this means, in a broader sense, is that the fossil record we have is not the fossil record that exists. It is a tiny, biased, accident-shaped sample of the animals that actually lived. Paleontologists have estimated in various ways that the known fossil record captures only a small fraction of the species that have existed on Earth. Some estimates suggest that we have described perhaps 1% of all species that have ever lived, and that is probably optimistic. The vast majority of animals that have ever existed left no trace we can find. They lived, reproduced, died, and were erased by time, chemistry, and geological chance. For every Henodus we know, there are almost certainly dozens of equally strange, equally interesting animals that lived and died without leaving a single bone in a discoverable state. Entire lineages, entire evolutionary experiments, entire chapters of the history of life gone without a record. We will never know what they looked like, what they ate, how they moved, what problems they solved, what convergences they embodied. They are simply absent from the story, not because they were unimportant, but because preservation is not fair and discovery is not complete. This is a genuinely humbling thought, and it is worth letting it settle rather than moving past it too quickly. When we look at the fossil record and try to reconstruct the history of life, we are working with incomplete evidence, not slightly incomplete, but radically, fundamentally incomplete. The picture we have is real, and the science built on it is rigorous, but it is a picture with enormous gaps. The animals we know about are the lucky ones, the ones whose bones happen to end up in the right kind of rock, in the right kind of place, at the right kind of time for someone to find them. Henodus is one of those lucky ones. And because it is, we have access to something genuinely remarkable, a window into a world that was already 230 million years old when it was sealed into limestone, a world of warm, shallow lagoons and hypersaline water and flat-armoured reptiles moving slowly across the bottom in search of whatever their strange beaked jaws could process. A world that no longer exists anywhere on Earth, that cannot be visited or observed directly, but that can be partially reconstructed from a single, nearly complete skeleton sitting in a museum in Tübingen. There is something quietly moving about that, if you let yourself think about it for a moment. The animal lived its life. It did not know it was remarkable. It did not know it was a demonstration of convergent evolution, or a puzzle for future scientists, or an argument about the deep logic of natural selection. It was just an animal, doing what animals do, finding food, avoiding danger, moving through its environment, existing in the particular way that its particular body allowed. It had no awareness of the 230 million years that would follow its death, no awareness of the limestone that would slowly replace its bones, no awareness of the quarry workers or the paleontologist or the scientific literature or the laboratory in which its skull would eventually be CT scanned. It simply lived. And then it died. And then it was preserved by luck, in a way that allowed us to find it and study it and think about what it means. That gap between the animal's life and our understanding of it is one of the things that makes paleontology feel different from other sciences. There is no way to go back. There is no way to observe Henodus directly. Every conclusion we draw is inferred from bones, from comparative anatomy, from the chemistry of the rock, from the behaviour of living animals that share some features with it. The science is careful and rigorous, but it is also, at some level, an act of reconstruction, a patient attempt to reassemble a picture from fragments, knowing that some of the pieces are missing and may never be found. And yet the picture that emerges is surprisingly detailed. We know roughly what Henodus looked like. We know where it lived and something about the conditions of that environment. We have reasonable hypotheses about how it fed and how it moved. We understand its place in the evolutionary tree of Triassic marine reptiles. We can explain, at least in broad terms, why it came to look the way it did, and why that shape appeared independently in a completely different lineage millions of years later. For an animal known from a single specimen found nearly 90 years ago, that is a remarkable amount of knowledge. It is also, of course, incomplete. There is still no consensus on exactly what Henodus was eating. The soft tissue is gone, the coloration is unknown, the behaviour is inferred rather than observed. Whether there were more specimens in other deposits, waiting to be found, is an open question. Whether Henodus lived alone or in groups, whether it came ashore to lay eggs or gave birth in the water, whether it was more active at certain times of day, these things are simply not known and may never be. But that incompleteness is not a failure of the science. It is the honest condition of working with the past. The science has done what it can with what it has, and what it has produced is genuinely illuminating. The story of Henodus is not a story of everything known. It is a story of careful, patient inquiry into a single strange animal, using every available tool and arriving at a picture that is partial but real. That, in a way, is what science at its best looks like. Not a triumphant unveiling of complete truth, but a slow accumulation of careful understanding, built piece by piece, revised when new evidence arrives, honest about what remains unknown. The CT scans of the skull added something that von Huene's original description could not provide. The phylogenetic analyses of the 1990s and 2000s clarified relationships that earlier researchers had only roughly sketched. Future work. Perhaps another specimen. Perhaps new analytical techniques. Perhaps a re-examination of the existing material with better tools. We'll add more. The story is not finished. It is just at a particular point in its telling. And for now, what we have is enough to be genuinely grateful for. A flat, armoured, beak-jawed reptile roughly a metre long, living in a warm hypersaline lagoon in what is now southern Germany, 230 million years ago. Not a turtle, but shaped by the same pressures that would later shape turtles. A quiet, slow-moving animal, built for the bottom of shallow water, carrying on its back a mosaic of interlocking bones that took millions of years of selection to produce. Found by a careful scientist in a limestone bed that had been waiting patiently for nearly 250 million years. There is something deeply satisfying about that image. Not dramatic, not loud, not demanding of attention. Just a flat animal on the floor of an ancient lagoon, doing its slow work in the warm salt water, unaware of the long future in which its bones would eventually be examined, described, debated, and used as evidence in arguments about the nature of evolutionary possibility. If you have been listening all the way to this point, thank you, genuinely. This is the kind of story that rewards patience, not because it builds to a dramatic reveal, but because the understanding accumulates slowly, the way sediment does, layer by layer, until something solid has formed. Henodus is not a famous animal. It does not appear in popular dinosaur books or on the walls of natural history museum gift shops. It is a specialist subject, a paleontologist's quiet fascination, a single specimen in a drawer in Tübingen that most people will never hear about, but it deserves to be heard about, because it carries in its bones a lesson that extends well beyond the Triassic, well beyond placodonts, well beyond the question of what a particular reptile was eating in a particular lagoon a very long time ago. It carries a lesson about how evolution works, about what the history of life looks like when you look at it carefully, about the deep logic that runs through the apparent randomness of the natural world. And it carries, perhaps most quietly of all, a lesson about the fragility of knowledge itself, about how much depends on the right rock, the right place, the right person, the right moment of attention. We almost didn't know about Henodus. We almost lost it to time and stone and the indifference of geological processes. We didn't, and because we didn't, we have something worth knowing. If this kind of quiet, careful exploration is something you find yourself returning to, it would mean a great deal if you like this video and subscribe to Life Beyond Seen. It helps this channel find the people who are looking for exactly this. Long, unhurried stories about the strange and remarkable things the world contains, told at a pace that lets you actually think about them. There are more of these stories to tell, and I would very much like to tell them to you. For now, though, let Henodus rest. It has been resting for 230 million years already, and it seems content with the arrangement. Somewhere in a limestone formation in southern Germany, in a layer of fine-grained rock that remembers a warm, shallow sea, there is the echo of an animal that was not quite what it appeared to be. Not a turtle. Something older, stranger, and in its own quiet way, more interesting. An armoured traveller from the deep Triassic carrying a message it did not know it was carrying, waiting patiently for someone to read it. Sleep well tonight, wherever you are,